Okay, it's 8:52, so I think we're going to go ahead and get started. My name's Allison Baker. I work here at NCAR. I'm in the Computational and Information Sciences Lab. I'm happy to see so many of you here, and if I haven't met you before, I'd love it if you introduced yourself to me at some point. I'm a co-organizer, and then Alper Altuntas was the other co-organizer, but today is really Alper's show. He did most of the work, all the work, together with some of the committee members for the tutorial. So I'm going to go ahead and hand it off to Alper, and we'll get started. Welcome, everyone.
Thanks, Allison, and welcome, everyone. So today will be the tutorial portion of this event. Tomorrow and on Friday, we'll have the workshop portion. So the tutorial is titled Rigor and Reasoning in Research Software. And our workshop is about correctness and reproducibility for Earth system software. So the goal for this event is basically to provide a dedicated forum for Earth system modeling, but also for broader scientific software community to discuss challenges, opportunities, and recent advances in ensuring reasoning about software correctness and reproducibility. And I'll start by acknowledging funding support from the Better Scientific Software Fellowship Program. I was picked as one of the fellows for this year's program, so the funding that we received has been used to organize this event. We'll also acknowledge general support from the CGD and CISL laboratories. So Allison mentioned we are organizing this event together with the help from our committee members I'm listing here. And also we received tremendous help from our admin team. Sam, Elizabeth, Teresa were great help and made this event possible. So before we start the event, I will mention a couple of things. First of all, we have this code of conduct, which applies to all the participants. So just to highlight a few things, please be considerate, respectful, collaborative, and value new ideas and opinions. So again, today will be the tutorial portion, and we've shared the links to the materials. And if you haven't received those links, please let us know and we'll share again. But the slides and recordings will also be posted after the workshop. And today we'll have 2 breaks, mid-morning and mid-afternoon. And I'll quickly share the schedule for today as well. But during the tutorial and during the workshop, all are encouraged to participate. So if you're remote, please use this raise hand feature, and a moderator will call on you. We'll also monitor chat, so you can type in your questions as well. And if you're in person, we have these ceiling microphones that will pick up your voice when you want to comment or ask any questions. So yeah, we'll have lunch on Wednesday and Thursday as a self-pay setting in the cafeteria. So you'll go through the line. And we have some options: hot lunch, sandwich, burger, salad bar. And we're going to have a reserved seating on the east end of the cafeteria. On Friday, our cafeteria serves at a reduced capacity. So what we'll do is we'll actually provide lunch, and there'll be options for dietary restrictions, again, at the east end of the cafeteria. Tomorrow, we're going to have a happy hour down the hill at a place called Southern Sun. Here's the address, and we'll try to organize some, how to get there. If you need a ride or if you can provide a ride, just let us know, and we'll meet at the NCAR lobby here, Mesa Lab lobby. Okay, so here is the schedule for today. I'll kick off with an introduction talk where I'll introduce some, fundamental concepts, some ideas that will be common across all these lectures that we will have. Manish will take over and give a guest lecture on unit testing. Then we'll have a break, and then Deepak will cover the property-based testing lecture. After lunch, we'll have a formal verification lecture, which was initially scheduled to be given by Phil Zucker, but unfortunately he had to cancel his trip, so I'm gonna cover that lecture. And then after break in the afternoon, Adrianna will take over and she will give a lecture on functional testing, and she'll also lead the practical session where she'll talk about how all of these ideas, all of these techniques and principles apply to actual real-world applications. So tomorrow we'll have a joint session of tutorial and workshop in the morning session. The theme there will be verifiable and explainable AI. We'll have a keynote by Soonhoo Kang from Amazon who'll talk about verifiable AI and their applications there. And then we'll have 2 invited talks by Antonios and DJ Gagne. And then again, those will also be on verifiable, explainable AI and reasoning. And then we'll have a panel moderated by Dorit. And that will conclude the morning session. And then in the afternoon, we're gonna have workshop contributed talks. On Friday, the last day of this event, we'll again kick off with a tutorial session. Helen will talk about GitHub workflows and how we use or how we can configure CI testing, automated testing. Then we'll have, again, workshop contributed talks in the morning and in the afternoon sessions. Okay, so with that, I think I'm ready to kick off the tutorial. So this is the GitHub repository that we will follow. This repository has the notebooks that we will follow. And you have a couple of options, including the binder launcher here. And also, if you have installed or downloaded this repository, you're able to run all these notebooks locally. But before we're actually going through these notebooks, what we'll do is actually, I need to switch back to these slides. So, okay, so again, our title for today is Rigor and Reasoning in Research Software. We'll mainly look at testing and verification techniques. But before we go through those techniques, I'll talk a little bit about these things: abstraction, decomposition, and specification. And we'll introduce these ideas to facilitate, to streamline testing and verification efforts. Okay, so why are we here today? Why all this matters? Well, because I guess I don't have to convince anybody in this room, computational science is really critical for scientific inquiry. In fact, it's now long been recognized as one of the pillars of science alongside theory and experiment. And so it's critical to have integrity in our software, computational software. So the goal here with this tutorial is that we'll explore how to make scientific software reliable, understandable, and robust. And we'll aim to do so without losing the creativity and speed and efficiency that really make research exciting. So something that's commonly encountered in scientific software is what's called the code and fix style, where we write code to quickly get results, fix issues as they appear, and then hope that all that holds together. And usually that's the case. Most of the time, our code works, but it's fragile and hard to test and really tricky to extend when the next research question comes along. So this tutorial is really about how we can break that cycle. And what we are going to argue for is this scientific mindset, which is based on the idea of refutability. We deem a theory to be scientific if it's refutable. And so similarly, we can build scientific software if it's refutable, if it's testable and verifiable. So we'll go over how we can achieve that, including practical techniques for how to hypothesize the behavior of our code, how to refute our understanding of our code, and then how to refine the code towards better understanding, better reliability and robustness. So this is in line with a perspective from Robert Martin, one of the pioneers of the agile method, who says software is like a science. We show correctness by failing to prove incorrectness. Basically, we show correctness by testing our software as best as we can. And such proofs of incorrectness can only be applied to provable programs. And so how do we end up with provable programs? We decompose a program into a set of small provable functions. So really, the decomposition step here is key to verification, testing, reasoning. So I'll say a few things about how we decompose our code. And first of all, we start with abstractions. Abstractions are key concepts in our software corresponding to things like key structures, relations, features, and so on. And so we decompose our code into modules, classes, methods, functions based on those abstractions, such that each part, each function, for instance, has an isolated, clear purpose, exposes well-defined interfaces, and each of them are refutable, testable. And so decomposition is really the central software design task, and that's really a broad topic. That's something that we cannot fully capture in a one-day tutorial or in a few slides. So what I'm going to focus on here is some few key principles for decomposing a large monolithic function routine into smaller functions that facilitate testing and reasoning. And here, the principles that we will try to achieve is, first of all, each procedure should have a single purpose. It should do one thing and do it clearly. These functions should be general so that they can be reused. We should avoid any hard-coded values or assumptions. We should have clear, explicit interfaces, narrow interfaces that's small, coherent, well-documented. And there's this idea of dependency injection where we pass in policies and strategies. And in his lecture, Manish will talk a little bit more about that and what that means and how that works in practice. And after going through abstraction specification step, what we do next is, after abstraction and decomposition, what we do next is specification. Once we have those modular pieces, then we need to say what each of these ones should do in a precise manner. A specification is a precise, refutable, testable statement defining the properties, conditions, or constraints that you expect your code to hold, and what behaviors or outputs should result from those given inputs. And there are a broad range of levels of specification, all the way from the system level to module, class, or function level. And in this tutorial today, we are mainly focusing on function level considerations. So we will focus on function level specification. So what are we going to specify? We're going to specify assumptions, expectations, like background facts that we take as given, some contracts of our functions, including preconditions, postconditions, and then some properties that we inquire about, like logical properties, computational properties, or physical, scientific properties. So to make things a bit more concrete, here I have a simple small function that divides x by y. And what I mean by contract specification is, so here we have a precondition saying that y should be a non-zero value, and then a postcondition that checks whether our computation is correct or not. So that's what we mean by, a specification or a contract in the simplest sense. So how are we going to specify these properties, contracts or assumptions or assertions? We'll use a practical style of specification, mainly relying on type annotations in Python and assertions. And the nice thing is that the testing frameworks that we're going to use today, PyTest for unit testing and Hypothesis for property-based testing, they both depend on assertions for checking the correctness of our code. So that'll come in handy in the following lectures. So why do we specify at all? Well, because these reasoning artifacts, assertions, ease testing efforts. It's much easier to test your code when you precisely specify what it should do, what the assumptions are. And it's also easier to change your code when you have those specifications in place so that you can safely evolve or replace your implementations. And there's also this added benefit that when you think rigorously about your intent and write it down, your reasoning and understanding improves a lot. And here is a quote along those lines saying, writing is nature's way of showing you how sloppy your thinking is. So it's really good idea to write down, you know, what you are intending to do. So after going through decomposition and specification, now we are really ready to implement our code that satisfies those things. And so this is a shift in our mindset. Normally we would start with lines of code, but now we are starting with abstractions and expectations and specifications, then fill in implementations that must meet them. After going through the coding process, now we're ready to actually test and verify our code. This is the refutation step and the final step. But and the majority of this tutorial will really be about this step. We will be talking about these different testing and verification techniques, including unit testing, property-based testing, bounded formal verification, and functional testing. So just to summarize these steps, we begin with abstractions and decompositions. We organize our code. Then we specify some properties, some assumptions, and then we fill in the code. We implement what we are planning to build, and then we test and verify. So this summary might look like we're suggesting something along the lines of waterfall method, which is actually an outdated way of developing software based on starting with a big design up front and then having these separate steps. But the initial design of a system or a component is almost never the best one, and experience shows us better way to do things. So what we are actually suggesting here is something more incremental, where you have tight loops, you have quick feedbacks, and you go through these steps incrementally and in an agile way. And the way to achieve that, to enable incremental design and development, what should be done is, again, tight feedback loops. Later work implementation tests can challenge and should challenge, refine earlier choices like abstractions and decompositions or specifications. You might realize that your specification is the wrong part in your software. So the other ingredient here is to move in small slices, specify just enough, implement just a bit, maybe just a function, and then test it and revise and go back and forth along those steps. And how this works, how this can be enabled is through these principles and ideas we are suggesting here. We should have clear abstractions that are easy to change, that lead to easy to change parts. We should have clear, stable interfaces so that refactoring is easier. We should have specifications, contracts. Those will serve as instant oracles so we can make quick changes. And we're gonna have fast unit property-based tests. So those will also serve as quick checks. So in the remainder of the tutorial, in all the lectures, we will have a running example, which is this simple example, 1D heat equation that we will use as a common theme across all these techniques. And it's this simple partial differential equation simulating the diffusion process in a one-dimensional rod. And what we'll do is we'll compute or we'll solve this equation using a finite volume approximation where we will discretize that one-dimensional rod into these individual cells, and we'll compute these three quantities. The first one being the diffusive flux across these cells. The second one being the divergence at cell centers, divergence of those fluxes. And then we'll update the cell average temperature as a final step. So this is one single time step. And here's a quick implementation of this example. We are starting with some initialization. We are allocating some arrays corresponding to flux, divergence, and the temperature array. And then we have this time stepping loop where we apply the boundary conditions, compute the fluxes, diffusive fluxes, and then we have this divergence computation followed by the update of the cell averaged temperature. So it's quite straightforward, it's quite manageable, a simple function that computes this example. But at the same time, it also allows us to observe and generalize some issues regarding testing and reasoning. First of all, there's no clear abstractions here. What are we modeling? What are the data structures? What are the concepts or relations? Those are not explicit, so it's hard to reason about them. There's no reasoning artifacts. We don't have any assertions. We don't have any property specifications. We are not testing anything. There's no contracts. And there's this single function that mixes concerns. One function handling multiple things, including computation of the boundary conditions, computation of all those different physical quantities. So it makes it hard to inspect intermediate results along our computation. The state is opaque and hard to reason about, hard to inspect intermediate results. And we don't have any reuse or substitution here. All the computations are tightly coupled. And so let's say we want to extend this code to also simulate the diffusion of another quantity, not just temperature. And in this setting, it's quite hard to do so because we have these implicit assumptions that all we're doing here is for temperature. So there's those implicit assumptions. And it's hard to reuse code here without any major refactoring. So this is only 10 lines of code. You might wonder, why are we looking at these issues, which are insignificant in this case, just 10 lines of code, and they are not consequential. But the aim here is really to discuss some strategies and some techniques that we can generalize to real applications. In the real applications, all these issues, all these same patterns will appear in functions with hundreds or thousands of lines of code where these shortcomings will actually become real barriers to understanding, testing, and reasoning. So what I've shown, the code I've shown initially is this monolithic code function that mixes concerns, that's hard to test, that's hard to extend, and it lacks some explicit reasoning that we can use in understanding what we're building. So what we're gonna want to end up with is separation of concerns. We want to separate our concerns. We want to explicitly specify our expectations. And then we want to structure our code so that we can understand it better, we can test it and extend it. So I'll go through all those steps quickly to show how we transform that initial code into something that we can actually work with. And that will be the version that we will use in the following lectures. So abstraction is where we decide what matters. Since this is a simple problem, it's really apparent what we need to capture. The concepts will include mesh, the domain geometry, which is a collection of cells. So we will need to capture that in our code. there is also this distinction between cell fields, quantities stored at the cell centers, one of them being the average temperature, but there's also the divergence term. And then there's also interface fields. In the simplest case, we only have a single interface field that is the diffusive flux across these cells. And then we are going to capture the computations, those 3 computations. And here, what we're doing then is we've just identified the key concepts that we need to capture that define our simple system, and then we're focusing on what we represent. We're not thinking about how we encode these computations yet. We are thinking about how we are designing, how we are organizing our code with starting with these concepts in mind. So here is a simple data class capturing our first concept, the mesh concept. Again, this is uniform one-dimensional mesh, and things are simple here. We have this data member dx that corresponds to cell size. We have the number of cells that determines the size of the mesh, and then we have these 2 helper functions, cell field and face field, that return 0 initialized vectors, arrays, that we can use to store data that are incident on either cell centers or alongside the interfaces. So one quick note, the code, the techniques that we'll show will again mostly be based on a function, it will be at the function level. And so the abstractions here we show are based on what's called the procedural abstraction, where we use mainly functions to organize our code. So we won't rely much on object-oriented features beyond this simple data class, but the principles, the ideas that we're sharing here also very much applies to object-oriented programming as well. So now that we know what we need to capture, the concepts we need to capture, now we're ready to decompose our code. We'll organize our code by splitting computation along those abstractions. And each procedure is going to have a single clear purpose. These procedures will be general, where we'll avoid hard-coded assumptions, or we'll keep things simple but composable. So what that means is, so we'll first specify this core API. Again, this is not about coding yet. This is about how we organize our code. And we have these 5 functions. First one for applying boundary conditions. The second one is going to compute diffusive flux, then the divergence. And the fourth one is where we put all those 3 computations together. That's the time stepping step. We're going to use an explicit Euler method. And then finally, the main function that we'll call the time stepping step, however many times we want the simulation to go on. So a quick naming convention here. We will use C for cell fields and F for interface fields. And underscore out suffix is for output arguments. Underscore inout suffix for both input and output arguments. And the reason we have these general argument names is in anticipation of using these functions for quantities beyond temperature. So we could, for instance, use, instead of C, we could use T or temp as our argument name, but that would implicitly restrict us to only use that function for a specific quantity, and that's not necessarily something that we want to have in our code, because we want to enable reuse. And this is all in line with a design principle called programming to an interface, not an implementation. But in the interest of time, I won't get too much into this. But what I'll talk about is specification. Now that we have organized our code, we've split computations into functions. Now we need to say what each of those computations need to have as preconditions and postconditions and properties. And here is one such example for the divergence computation. Quick structural assertions. The first one checks that our arguments have compatible sizes. The second one checks that our mesh size or cell sizes actually make sense. They are positive. So quite fundamental checks. And beyond these fundamental contracts or structural correctness consideration, we will also express some logical, computational, or physical scientific properties. And in the case of heat equation solvers, just to name some properties that we are going to check in the following lectures. The first one is the telescoping property, where we are checking whether sum of the divergence across all cells equals the heat flux that we get from the boundaries. It's something intuitive that you would expect to hold. And then the conservation property is another consideration that we're going to check. Does the total heat remain constant? And then we'll check some other properties, intuitive properties like symmetry. If you start with a symmetric initial conditions, and if you have anti-symmetric boundary conditions, do you maintain that symmetry? Of course, since this is a diffusive process, things will smooth out, but that should not break symmetry. And we'll check whether that's the case, just as exploration. And then there's also the property of monotonicity, where we'll check whether this diffusive process actually introduces new extrema, which would be against our understanding of the diffusive process. So I'll only talk about one of these properties in these slides. That's the telescoping property that we will get back to at each lecture. So the idea again is we're gonna sum the divergence over all of these cells in our mesh, and we'll check whether that equals the net flux through the boundaries. And here is a function that actually specifies this property. And the reason we're able to specify this property in a compact, practical manner is because we have this isolation of concerns. When we organize our code, we have well-defined APIs, isolation of concerns, that actually facilitate specification and testing of these properties. And first we compute the total divergence, the boundary flux, and then we check whether they are approximately equal. And since we're working with floating point arithmetics, we need to take that into consideration. These kind of checks need to be approximate because of the floating point precision issues. So after going through the specification, now we're actually ready to write down our code. We have identified our abstractions, decomposed our code, and wrote some specifications. Now we're gonna implement the code. And I'll quickly go over the core functions here. The first one is the diffusive flux, where we are computing this flux across each cell. Quite straightforward. And the divergence, again, is this simple equation, that formula that we are computing here for each cell with some assertions, some preconditions. And then the time-stepping loop, or time-stepping function that calls boundary condition, diffusive flux, and divergence functions, and then updates the average temperature over the mesh for each cell. And so those are the core functions that we will focus on in the following lectures. But yeah, so in the remainder of this tutorial, we'll look at these testing techniques, and we'll cover unit testing, property-based testing, bounded formula verification, and functional testing with some hands-on exercises. So I'll just preview all of these techniques quickly just to set the stage. First, we'll start with unit testing. The idea here is quite simple. We call our units, our functions, with some inputs, and we check whether we get the output that we expect. In this case, I assert here this telescoping property and check whether the inputs I give satisfies or entails this property. And Manish will talk about how we write unit tests and how we use a testing framework called PyTest to automate and to streamline these kind of tests. And the framework we'll use is called PyTest, and you're going to write some tests, and then this framework will automatically check these properties through the command line. And unit tests are quite practical, quite useful. They are great for quick, focused feedback. They really enable these tight feedback loops. And I never heard any thing against unit testing. Everyone argues that it's a best practice. But one limitation is that they only test the examples that you think to write. So there's always this chance that you might not be able to think about some corner cases, some edge cases. And that's where property-based testing comes. Deepak will talk about this technique that's beyond unit testing. It's actually the same idea. We are, again, focusing on functions, some units. But what we do is we auto-generate these many random inputs to explore cases that we might not be able to think. And the main idea is that we specify some preconditions, some input space, and then check whether some properties, some relations that we expect holds for all those inputs that we receive from that input space that we specify. And this random generation of inputs, it can be made smart by guiding them through strategies, through constraints, to target edge cases. And one cool thing about property testing is that when it finds some counterexample, it tries to shrink the counterexample to make reasoning easier. And I'm sure Deepak will talk about these more in detail. But just to demonstrate this telescoping property check, we'll use this hypothesis framework. And what it does is it just calls our units, our functions, with all these random values just to break our code, just to break our property that we specify. So one other testing technique that we'll cover in the afternoon is what Adrianna calls functional testing, where we will try to apply this mindset, these ideas, these techniques to a Python version of a production code, an actual application, not the heat equation solver, but an actual wildlife behavior simulator translated from Fortran. And we'll explore some scientific representation. The idea here is similar to property-based testing, where we will use some synthetic inputs to probe our scientific code. So these are all testing techniques that are quite useful, quite powerful, quite effective, and practical. But again, there's this downside. Testing can be used to show presence of bugs, but never to show their absence. We are never sure that we have code that's correct, because there's always the chance that we might miss some corner cases, some edge cases. So what we are going to explore beyond testing is what's called bounded formal verification. Here, we will shift the paradigm a little bit. We'll symbolically check whether our properties hold for all possible inputs, not just select either random or hand-picked inputs. And we'll do so within some specified ranges. That's why we're calling this bounded. This is, of course, less practical, but because there's this element here, we need to model our code in a declarative way, in a symbolic way, but it's still achievable when we have the right level of abstractions and decompositions. If we follow those design principles, then this technique can also become quite practical and achievable. And by reasoning symbolically, what we do is we move from testing some cases to proving, actually mathematically proving all cases. And this gives us what's called scope completeness. The solver that we're going to use will explore every combination of inputs. And thanks to what's called the small scope hypothesis, which says a high proportion of bugs can be found by checking the program for all inputs within some small scope. So this hypothesis makes this kind of approach quite powerful in uncovering subtle bugs. And the tool we'll use in this lecture is called Z3. It's a popular formal methods tool used across many domains in academia and industry. And it's used for a broad variety of applications, ranging from bug finding, verification, constraint solving, compilers and optimizers. I think, in fact, LLVM uses Z3 to check the equivalence of optimized code compared to the non-optimized code. And it's also used for tool development. For instance, if you've ever heard of Visual Case Gen, this is a graphical user interface that we developed to streamline the configuration of our Earth system model, CESM. And we use Z3 under the hood in Visual Case Gen to reason about model configuration, setting compatibilities, or for detecting conflicts, explaining incompatibilities. So this is all to say that Z3 is quite powerful, quite efficient, and also has many broad application areas. So tomorrow's keynote is also about formal reasoning. In this case, formal reasoning applied to AI ML. Sunhu, our keynote speaker tomorrow, will talk about another formal methods tool called Lean. That's also a theorem prover like Z3, and that's also developed by Microsoft Research like Z3. And Sunhu is, in fact, one of the core developers of this tool. And he'll talk about how they use Lean, formal verification at Amazon, to reason about AI ML correctness and how AI and formal reasoning are coming together to make systems smarter and trustworthy. So in the final few minutes, I'll just try to conclude. First, just look at these different techniques just to compare the way they cover the input space. Here, think of X and Y axes as problem size. In the unit case, in the unit testing case, we are generally looking at these hand-picked small problems. In the case of property-based, we're basically probing our code with all these random test cases just to see if there's any edge case or corner case that we couldn't think of in the unit testing phase. But then there's also this formal verification, theorem proving aspect, where we again limit ourselves with some small problems. But the nice thing about this technique is that even though it has a small scope, it covers all possibilities within that scope. So that's the power that it brings. So none of these techniques is a one-size-fits-all solution. Each of them have their own trade-offs in effort, scope, assurance, confidence. Unit test is essential. We should have unit tests in our codes almost always because they are fast, focused. Property-based testing is broad, exploratory. It's quite efficient, quite powerful. Formal verification may not be as practical as the other two, but when we need that extra confidence, it can pay off. And depending on your project's needs and practical constraints, what we argue is you choose these or other techniques that we don't cover here. But what we really argue is something beyond these tools and techniques. It's a scientific mindset where you start by thinking about the abstractions, the properties your code should hold, and you hypothesize about those properties through reasoning and specification, and then you attempt to refute your understanding of the code through testing and verification, then incrementally refine your code and your understanding based on those results. Okay, so does all of these extra work slow us down? For one-off application, yes, that's going to slow us down. It's extra work. But for code that would live beyond just a few versions, it really pays back because it enables quick inquiries, it enables fast changes, and it enables exploration of new ideas. When we want to explore a new scientific direction, having all these things in place really help us in the long run. So with that, I will stop. And if there's any questions, I can take. But otherwise, Manish will take over and talk about unit testing.
Does anyone have a question?
Okay, so yeah, thanks, Alper. That was great. I was just thinking, this is maybe just kind of a design opinion question, but like I noticed in your division example, which I realize is a very kind of silly example, but you know, when you make it verifiable, you kind of specify the types, but I guess you would lose type polymorphism a little bit, right? Because now the previous one could take integer or floats or whatever. But so if I wanted to build a function that was type polymorphic, with the general idea being like maybe the very first thing I do is check types and then kind of send that info to the relevant function or class that's associated with it.
Absolutely. So what you're suggesting is we would have this wrapper function that would call, you know, appropriate functions just like we do in Fortran or C++ kind of thing. Yeah.
Sure. I mean, I guess I don't know if that's like in Python. I'm not as careful with my types in Python. So like, yeah. So I just but so I'm asking as general, yeah, should I be kind of trying to do that where I'm doing more type checking and
Yeah, that's probably getting more into, you know, API user experience or, you know, developer stuff. But yeah, so the thing is that when you have integer division versus floating point division, real division, you're gonna have different sets of preconditions or postconditions. So yeah, we need to kind of separate them. But from a convenience point of view, having a wrapper function calling different ones, yeah.
There's a discussion, Alper, online about if I think I lost the first question, but if fuzzing was a similar idea to property-based testing. And there's some answers up there, but I don't know if you want to comment.
Deepak, would you like to take that question? Is fuzzing the same idea as property-based testing?
I think the answers there are good. They're very similar. I agree with the property-based testing is a little more targeted. And the tutorial that we'll work on, I kind of emphasize how you should think about the space of inputs that are generated. So it's not fully random. There is some targetedness to it.
Any other questions? Okay, Manish, do you want to?
All right, hi everyone. We're going to be taking a slightly different approach to this lecture, and it's going to be a little interactive. So there's plenty of opportunities for this to go wrong. So if you haven't already and you'd like to follow along, and you don't have to, please pull out your computer. You should have gotten an email from Alper and Sherry a little bit ago about their GitHub repo, and I'll just actually go there really quickly. This one right here, R3SW and Alper Alltuntas. What we're going to be doing in this lecture is we're going to be going over one of the notebooks here, and to do that you need to run the notebooks, and there's a couple different ways to do this. One, and I will be doing it this way, you can click this launch binder button and then open the notebook and it'll be all set up for you, or you can clone and run the notebook on your own computer, but just know that you'll have to have PyTest installed for at least this lecture. So I feel like everyone already has a computer out, but if you'd like to do this, please set it up. All right. And we're going to be going over chapter 3 in the notebooks. Okay, great. So this talk is going to be about unit testing. And it may be familiar to some of you, but I just want you to know there's going to be a quiz at the end, so please pay really, really close attention. But what we're going to do over this talk is we're going to briefly talk about unit testing and then work through some examples with the 1D heat solver that Alper talked about. And what we're going to try to do is talk about some of the benefits of unit testing and then try to feel out what are some of the limitations are so we can kind of expand or like think a bit more about what Alper just talked about here. So with that, I'm going to get right into it. So unit testing, it's a pretty common software technique where we're testing individual code components, basically these units in isolation from everything else. So what we're going to do in unit testing is take each of these individual units and put a lot of inputs and outputs against them in our unit testing. And to do that, you're going to need a few different choices in your code to actually run unit tests. You can't just do this if you don't think about it first. And that comes up in a few different ways into these 4 first topics here. To write unit tests, you need small cohesive functions, i.e. those units of code. And it needs to do one thing, right? You don't want it to do multiple things because then it gets harder to test. The other thing that you're going to want to need to do unit testing is explicit interfaces. So you need to have well-defined inputs and outputs to run interfaces so we know what goes in and out, which is just kind of straightforward when it comes to testing. The third thing is that you want to avoid side effects in your functions. So if your unit of code is impacting global state, that pretty much makes a mess of your unit testing. You want to make sure you're avoiding that effect. And then finally, if you have dependencies in your code, you want them to be able to be injected as parameters. So you're not messing anything up like that. So once you set up your code this way and you actually do unit testing, there are some benefits to doing this. One, it helps you catch bugs early because you're testing individual components as opposed to your entire workflow. It also lets you facilitate code changes, which basically what that means is, and I'll scroll down a little bit here. Basically what that means is if you make changes to your code and you have a good suite of unit tests out, you have confidence that it's actually going to work. And then third, and this is a little bit more of a nuanced thing, is we talked about the fact that you need to do things to your code to actually do unit testing. Unit testing forces you to think about your code in a way and to structure it into these small units. And then finally, we have documentation, which is the idea that unit testing kind of like shows you what's going on in your code. And most importantly, in my opinion, it also has expected outputs, which I think is part of documentation you don't always see. So those are some of the benefits. And that's it. That's the lecture's over. I'm just kidding. What we're going to do is run through a few examples of how you would do this using the Heat 1D solver. And how we're going to do that is we're going to take a very basic function, and that's going to be diffusive flux. And we've just redone it here. If you're following along, please do run all of these cells because that's how we'll be figuring this out. This is something Alper mentioned in his talk, and we're going to be trying to do a unit test of this function. And this is our unit of code. So I'm going to really quickly run it just so that's in my environment. And then we're going to try to write a test. And we've written one for you. In this test, right here, we have some constant fields, and then we have our output diffusive flux. We run our diffusive flux function, and then we check if it's all zeros, because constant fields, there's not going to be any flux, so we're completely fine there. And we can run it. And voila, we didn't get any output, which basically means it worked. And that's it. I can actually show it breaking, just so that you know that it doesn't just magically just not return anything. And that's great. So, oh, okay. That's a unit test. Are we done? Is that it? Is that all we need to do to test diffusive flux? We're done with our unit testing. Does anyone, I know this is crazy, but I'm gonna ask a question here. What are some limitations of having just this unit test? And it's like so fine if no one answers. Okay, so a limitation of this unit test is that it's only covering one topic. And I'm sure a lot of you are already very familiar with this, but what that means is we're gonna need to write at least one more test. We know that, like constant is not the only thing that's gonna work. So before we get into writing more tests, I'm going to introduce a framework that makes this whole setup a lot easier. And what that is PyTest. And maybe some of you are familiar with this before, but it is a way of cleaning up your unit test environment. It's the way I think about it. But when you do manual testing, where, for example, we're testing our diffusive flux function, we already know we're going to need multiple tests. And that can start to get very time consuming to set up and make sure all the functions run correctly. And it's prone to errors, right? Automated frameworks like PyTest, which we'll introduce, make that process a lot simpler and come with lots of powerful features that help your unit testing go well. Another popular framework is unit test, but we're using PyTest basically because it's simple and has a lot of cool features that we'll talk about in this lecture. And so a couple things to introduce PyTest. One, it's a command line tool. So we're going to be using the exclamation point to run command line commands in Jupyter Notebook. And we also need to write out our code into files, into Python files. I'm going to do that with this Jupyter magic called %% write file. So just keep that in mind. One thing that we're going to do first is we're going to load our 1D solver that Alper talked about in the previous talk. It's not too important. We're just going to run it. And what it does is it loads one of the files that's in this repo, the heat 1D solver that we discussed. And it has like the mesh and things we talked about. I'm just going to really quickly run this. So in the next little bit of this lecture, we're going to talk about PyTest, some of the features of it, and then try writing some unit tests for our heat solver along with some representative examples along the way. The first thing that we're going to talk about here is assertions. And so assertions in PyTest are how it tells you what's gone wrong, right? So when an assertion fails, PyTest is like, this is a failure of your test. And this is great because there's nothing extra complicated we have to do. And if you do, as Alper talked about, and have preconditions and postconditions in your code, your test doesn't actually have to be that complicated. You already have your assertions as part of your actual functions. One of the other things we're going to talk about here is that floating point comparisons are very brittle. So when we do things like compare floating points, we want to use something like pytest.approx, which is a way of making sure you don't break it, have that brittle comparison. So what we're going to do to first showcase this floating point issue is you come back to our division. Oh, okay. In our division example, there's a few things that we'll highlight here. One, we're going to be writing this file out and doing something called test_div. And then we have a precondition, which is y is not equal to 0, basically denominator is not equal to 0. We do our division, and then we check it, and then we return it as a postcondition. And then when we write our test, all we're doing is running the function with a random set of numbers. Those aren't randoms. Those are very specifically picked out. So when we, and that might be a limitation of unit tests if you're paying attention. Okay. When I set this up, what I've done is that I have my division function and I have a unit test for my division function. What I can do to run this in PyTest is I can run it on the command line with pytest test_div.py. And if you're following line binder, you should be able to run all of this straightforwardly. When I run this, what it does, and ignore the fact that it failed for a second, it sets up your test session and then it runs your test. And it seems like we have a failure. And so what's going on here in this specific case, if we scroll down to where the issue is, it's saying that our division didn't really work out. And that doesn't make sense because it's not very clear why it's happening. What's actually going on here is we're having this floating point comparison issue. So what we can do here to improve this, we can improve this function in a couple different ways, okay? One of the first things that we can do, and this is important in PyTest, is we can expect an error, right? We think we already know this is going to have an assertion error, so we can just say, here at PyTest, we know this is going to happen, so let it pass, right? And so we can do that with the raises context manager. And how that works is you import raises from PyTest, and you say, in our test, we expect that this division is going to have an assertion error. So if I write this out again, and I run it again, you should see it pass, which basically means we expect an error. And by the way, just to keep in mind that when we write out files, they're just showing up right here. There's no magic going on here. And this is fine, like, right? Like we got it to pass. That's, yes, I would love to. Okay. Is that a bit better? Okay. Maybe I can shrink this a little bit too. Oh, never mind. Okay. So this, as we said earlier, we're using raises assertion error. That's not ideal for the situation. Like we still want to actually test the division. So we can use this pytest at approx situation, right? So what we can do is we can import approx and then use it as a comparison for the floating point comparison we have here. So when I run this and then run it again with pytest, it'll pass the same. And we like that a lot better. So now that we've tried it on this very simple example, why don't we try rewriting our test? Did you have a question?
Function and sort of what its boundaries are, or like,
Yeah, Alper, you might know.
what is it,
You do like prox question mark so that we get back in place. Yeah, so.
This word. Yeah, so it's very similar to NumPy. It's close.
Errors, but there's one that's default. I don't know what that value is. If you can scroll up.
Yeah, I'm not sure. I'm happy to look at it a bit later. And see what it's like. But it comes with some defaults.
I guess you don't want to accept all, like, it's not obviously
Yeah,
not accepting
yeah,
all
yeah,
answers, or else it would like defeat the point, so it's got some
Yeah.
boundary, right?
Yeah, not sure. Well, we'll see what it is. Yeah. Okay. Apart from that, which probably should definitely have known, it works, and we can use numpy.close if you want something a little bit more explicit. So one of the things that we can do is we can try using pytest.approx with our diffusive flux, right? So we're using numpy.isclose before. Can we try this with diffusive flux? So I'm going to give like a couple minutes here, and we can try writing this function that we had previously, the simple test with the constant field, here using pytest.approx. So why don't we give like a minute here, and you can just copy the initial code and try replacing it. And I'll turn off this microphone. Okay, hopefully you've started to come up with some way of using approx. But I'm gonna just do it really quick, and how I'm gonna do this, I'm just gonna copy the initial test we had and replace the numpy.isclose with approx. And you can do this a variety of ways. Okay, so. What I'm gonna do here is do all right, hopefully that'll work without issues. And so what we're gonna do is we're gonna do the same thing where we write our test file and run it with pytest. Uh-oh. Indentation, okay, that's really embarrassing, guys. But this is why we have testing. And so, yeah, so we can use approx for this, and this is just a really basic example of using approximate. Okay, so you may have followed along pretty easily with this, but for pytest, how you run it is with the command line, and you can use approximate for floating point comparisons. And so how pytest is discovering these tests and actually running this function is in a pretty simple way. And I'm going to say test a bunch in the next 30 seconds, so just hang in with me here. Pytest discovers tests by looking for files that start with test underscore or underscore test.py or ending with underscore test.py. And in those files, it looks for functions that start with test underscore or classes starting with test, but we won't discuss that too much. So when I run pytest, what it's doing is looking at my folder here, and then it looks for these tests. And it looks in these files for something that says test underscore, and then it runs those. So now I can just run on just the command line pytest, and it will look for all of these tests and run them. And it looks like we have this secret test metamorphic that's mysteriously there. But it finds a test that we want through that. So that's how pytest discovers tests. So when you write your unit testing suite, you can name all your files test underscore underscore test.py and then name it with test underscore. So you can start as we get more into this. And like we said earlier, we want to write multiple tests for diffusive flux. This is one way of making it as easy as possible to run those tests without having to worry about how do you run this and mixing any errors. So that's the first introduction to pytest. The next thing that we're going to talk about is fixtures. And we're going to do live coding here because there are never bugs with this, okay? So for a diffusive flux, there's a few different things we want to test, right? More than the constant test, we want to test like a non-constant field. So I'm gonna try doing that initially. I'm gonna call this test df_1 because I have really good naming practices. But this is just a demo. And say I have a non-constant field. Actually, let me copy this ahead so we don't waste time with me typing. All right. Okay. So if I have a non-constant field, let's just say we use 0, 100, 0. I delete all this. Okay. And I test it like this. I expect it not to be 0. What I actually expect is for non-boundaries. Expect negative 10, 10. Okay, and that's just from the equation that we have earlier. And of course, I have to import PyTest, the approx function. And then we'll write it out. Write file, test, batch, pictures, .py. Okay, so this is a test where we have non-constant field and we're running diffusive flux and we expect certain answers out. Say, for example, I want to test this, but I'm like, wait, I want to make sure that my kappa, for example, actually fails if I put in a kappa of 0. What I might do here, and this is an I might copy and paste and be like, I expect an assertion error with raises, assertion error, when kappa is 0. And I'll fix the, right? So if I were to run this and I write my file, and bear with me, there's definitely going to be an issue here, and run my PyTest. Oh, okay. Oh, wonderful. Okay, so I forgot to import diffusive flux. But what I've done here when I run this is I've written 2 tests, right? One test where I've tested my spike condition, or not spike, but non-constant field. Another one when I've checked a different thing where I expect there to be an assertion error. And what's happened here is I've had to copy and paste this U vector, right? And so when I do that, that's just a waste of time. Like, we don't want to be copy and pasting and encoding. What we can do is actually save small pieces of state and use them across tests. And that is what a fixture is. So PyTest, yep. Oh, sorry. Okay. Now we have 2 tests. Thank you for that. So what's going on with these fixtures is that we get these small named pieces of test data that we can use across several tests. So for example, in our test here, we've written 2 tests where we set up 2 U vectors. And we don't always want that to be the case. So we can actually save them in a fixture and then use them in multiple places and not have to copy and paste it. So what we do for the Heat 1D solver is we've set up a bunch of fixtures to be used across the entire Heat 1D solver unit test suite. And we can do that in a few different ways. One, you can put fixtures in your test file, or you can put them in a conftest.py file, which is just one shared file that PyTest uses to share fixtures across several files. And we've just set that up here. Won't look too much into these, and these are pretty simple. They're just like constant values and one lines. But as you get more into more complicated test suites, there can be, you'll get more and more complicated fixtures. So I'll run this really quick, and this is just saving a file called conftest with all of our fixtures in it. Oh.
Can you scroll through them?
Yeah, of course. Yeah, so we have things like we're setting a certain DX and a kappa in some of our meshes and things like that. And we'll be using them in some of the tests later on. We won't talk too much about them. Okay. Yeah. All right. so that's fixtures. Another thing that we use in PyTest is marking. And so we're going to use a representative example for this. And we have 3 tests in this example. There's a test fast, which just asserts true. We have a test slow that sleeps for 3 seconds, and a test fail that just fails. So when I run this in PyTest, we get exactly what we might expect. And it looks like it's hanging for a second here. Okay, so it might hang for a second, but what's going on here is what we're going to expect is that the test fast passes. We wait 3 seconds for test slow. Oh, okay. Let's see. Okay. I'm going to try opening a new binder session. But it looks like I might not have Wi-Fi. Oh, we already loaded. Okay, so we'll still continue going through this lecture, and you might have to take my comments on truth because they don't run. But what's going on here is you get a fast, a slow, and a fail. And so that's all well and good. And as you write unit tests, you might have a similar thing where you have a test that is fast, slow, and it fails. What we can do with PyTest marking is mark your tests in a specific way so that you get expected failures, and you can choose to run tests that are maybe fast, that are slow, and are fail. And you can do that by adding an @pytest.mark with a specific mark attached. Say, for example, for the slow, I mark it as slow. Or for fail, I can use a default PyTest mark called xfail, which is an expected failure. And so, yep. The code, I don't know what that is. Yeah. Oh, collab. Okay, yeah. Okay. Oh, we have to go to the website, yeah? Oops. Uh-oh. Nothing, okay. Yeah. Oh, okay, great. All right, so you can also go to the thing through, if you go to chapter 3 unit testing, and we go into this button at the top, collab. And it looks like that might work. Okay. Okay. Great. So we'll do test. Hopefully this works. All right. Yeah. Okay. So back where we were talking about a fast, a slow, and a fail test. And what happened here, I'll run this again. What's going on is one passes, one takes 3 seconds, and one fails. So if I was interested in marking these tests to show that they are slow or they fail, I can use pytest.mark.slow or pytest.mark.fail, which is a default mark. So when I write this out and I run it, I can use something called like the M flag to run only the tests that are marked X fail. So if I run this, what it'll do, and ignore the warning for now, we'll collect all 3 tests and we'll not select 2 of them, and we'll only run the one that's marked X fail. For example, if I want the ones that aren't X fail, I can use not X fail, which is just a neat little feature PyTest has. And it's running, of course, the 2 tests, including the one slow one. The reason we're getting this warning is that some marks, you do need to register the marks inside of PyTest, and you can do that in a file called pytest.ini, and there's a bunch of different ways to do this with specific markers, but we won't show that here. But it's just a feature in PyTest that lets you pick specific tests. Say, for example, you only want to run a certain test, parts of your test, because you think those are the only ones that'll be impacted. So that's marking, and it's a pretty useful, yep. Yes.
I guess your X fail means it's expected to fail.
Yeah, and that is a default by test, so we don't have to mark that.
Oh, I see.
Slow,
Okay, so
there's
there's
a
some, so slow is one that you added, but there's a list of.
deep, I think there's 3 default ones. I'm not quite sure if you're doing it. So I can use slot, for example, and then write slot. And that will, and PyTest is smart enough to understand this, but you should register it as well. And it will just select the one that you want, the slow test, which are right. Yeah,
Okay.
yeah. There's a neat little feature. Okay, and the last
A kind of feature we'll talk about instead of PyTest is parametrization. And so we already talked about our constant fields diffusive flux. I know maybe we're sick of it at this point, but we also want to test our non-constant field. So what we can do with parametrization is parametrization allows you to put in a set of inputs and expected outputs. So you don't have to write multiple effect functions. And so what we're going to do here is we're going to actually kind of motivate this parametrization by showing you what if we wrote this non-constant diffusive flux text. So I'm going to give a couple minutes to try writing this non-constant test, and we've just put it here if you'd like to use it. And then I'll write it, and then we'll try to do it with parametrization as well. So I'm going to turn over my mic.
Yeah, I'll be writing this too. Oh, okay. Yes, Sam.
For those of us who are too slow to follow along, could we get a completed version of all these notebooks?
Yes, so if you go to, I believe the full notebook will be here after the thing with all the answers in there. Yeah.
Yeah, actually, and there's an answer right here as well. So there will be a full thing with more explanation in the comments as well, at least for this chapter. Okay, so there's a lot of different ways to do this. The way I did this, and you may have done this as well, is I copy and pasted, which is always, usually a sign something went wrong, of a non-constant flux, and then I just calculated what I expect the expected answer to be. And so when I run this, it works fine, right? I can run this and make sure that I get 2 tests out of it. Okay, never mind. No, oh, because I have to load the heat 1D. Okay, we won't worry about this too much, but basically what's going on here is that I had loaded the heat 1D earlier, but it doesn't work here because I'm in a separate situation. But what's going on here is we have a non-constant flux, and all I've done is copy and paste it and change 2 lines. And obviously, that's not going to work, which is where we get parametrization. Parametrization is another mark, and what you can do here is you can add inputs and expected outputs. And that's actually what we do with this modified function. We pass in a u, a kappa, and a dx, and an expected value, and then we can test it against several different inputs and outputs. For example, we have our constant value that we were talking about in our first example, then also a changed value, which is what I had separately with its own kappa and dx and its expected value, just using the same formula. So when we run this out and run PyTest, we get 2 tests with 1 function, and that's a pretty solid way of testing diffusive flux. So I'm not going to run it here because obviously heat 1D isn't imported, and I'm not quite sure what is happening, but if you're running on the Google the binder, it should work. Okay. One other thing is that the S flag allows you to print stuff out. So if you have print statements in your test, the PyTest is not going to show that. Using the S flag will let that happen. Okay, so those are the features of PyTest. We got marking, we got fixtures, we got assertions, we got parameterization, all that stuff. Now we're going to go back to something Alper mentioned, was the telescoping property. And this is the function for it, where we're checking the divergence against the boundary fluxes, and they're supposed to be the exact same. We're going to do one exercise, and this is the last exercise of the whole thing. And we're going to write a test against the telescoping property of the divergence function. All right, so we've already written some shadow code for you here with the telescoping function itself and where you're going to write your test. Try writing how you would write this unit test for checking the telescoping. property. So I'm gonna give you 2 minutes to do this, and then I'm gonna make sure that my heat 1D is working at the same time. And don't scroll down, the answer is right there. All right, so how we decided to answer this, because we already have a telescoping check and we already have our divergence function, all we need to do to run our test is just use pretty much random inputs and run our telescoping check within a search statement. And so we added our random inputs, we calculated divergence, and then we just pass it into our telescoping function. So when I run this and test it, you get a unit test. So that's just an exercise we did for telescoping. We've also provided a set of tests for actually testing the heat 1D solver. We won't discuss this too much, but it is worth looking at. In it, we include our fixtures and using the search statements and all that stuff, but we don't do parameterization or marking. But if I were to run this and then run it, you'll get some tests out of it. Okay, well, I also need to run my fixtures from earlier, but if you've been following along with the tutorial on one notebook, it should work. I'm gonna skip past this really quick and kind of summarize unit testing a little bit. We talked about some of the features of PyTest and how you use unit testing to start off with, but you may have noticed we bumped into a few limitations. For one, we have limited coverage. So the tests that you think about are what you're testing. As Alper said, it can show the presence of bugs, but it can't show all the bugs. Another thing is that unit testing can be very repetitive and tedious. And we have all these things like fixtures and parameterization to make it easier, but you're still writing a lot of tests. And as you get into more complicated projects, you're gonna have huge suites of unit tests. And then finally, and I actually run into this a lot, is overfitting. So in unit testing, if you're making small changes to code, you may run into this issue where you're having to change 6 tests just to make things pass, which kind of partly ruins the point. So those are some of the things that you can run into as limitations of unit testing. And of course, there are so many benefits, but it's things to think about. And as we get into the next few chapters with more other types of testing, it can start to cover some of these limitations. So with that, thank you for listening. Yeah.
Thanks a lot. Are there any questions in the room?
Tail? Does PyTest check the type annotations that you wrote in?
No, it is not checking that.
Okay. Is there,
No, go on.
I was just curious if there's a way to do that? Like if your test somehow violates the type annotation?
Yeah. If I was to take a stab at it, I'd probably just use search statements with types. Alper, do you know if there's any ways to check types in Python?
Yeah, there are like static checkers like MyPy or similar tools that actually confirm your type annotation.
Okay. So those, yeah, I guess the type annotations don't inherently enforce anything in the testing framework.
By default, yeah, it's
Just informational.
right.
If anyone online has a question, just type it in the chat. Jesse?
Sorry. Oh, I was real quick. Does PyTest, can PyTest do any kind of code coverage estimation, or do I need a different tool for that?
Yeah, I don't think so.
Cool. Thanks.
I have kind of a best practice question. If somebody else is gonna be using this code and you have these asserts in there, then if that fails, that's gonna give them this kind of random testing garbage that they're not gonna know what to do with. Is there a way to
Yeah, so
or something that's more understandable?
Like at the end of a search statement, it will also get output and it will give you the values that come out of the search statement. So that can help like tell you what's going on, if that makes any sense.
Sure, but I'm just thinking the way that this is like, testing output. I feel like sometimes it's nicer to have you, if you get this error, then contact this person or what it is, whatever it would be.
Yeah. I don't know if that's something you can do directly through PyTest, but you could add comments to like your search statement, like output, like if it fails, it returns this output. Like you could add like things.
Oh, okay.
Yeah, you might have seen that earlier in some of the places, like I think at the top. Like you could expect outputs this and you can put.
Oh, that actually is printed out.
That gets printed out. So when you have an assert measurement fail, it prints out the second part of your.
There's a comment online that for type checking at runtime, there's a package called bear type that uses randomization to check against type annotations in constant time. Thanks, Jennifer. Go ahead.
I mean, one thing you can do with the assertions is if you go, I can't remember what the command line option is, but in Python, you can just disable assertions when you run. So,
Slash capital S or
Yeah.
something like that.
yeah. So then, because then, you don't get the performance of checking it. But my other question was, I noticed that you included the approx from PyTest into your non-test files. I'm wondering if that's the best practice, adding a dependency to PyTest in a file that could stand alone from PyTest.
That's a good question. I tend to use NumPy. Alper, do you have any,
Yeah,
yeah.
yeah. Outside the scope of testing, we should be using this.
Yeah. And that's probably just because we have the tests in the file. Sure. We usually, yeah, and generally speaking, you put your tests outside.
Yeah, also a few questions about approx. Like, firstly, the syntax seems a little weird. Like, does it work only in conjunction with equality checking? Or because it seems to be like a function that can be called on a variable. That's number one. And the second one is like, does it use the same formula for like the relative and absolute tolerance thing as the NumPy all close, or is it slightly different?
Yeah, I will throw that to Alper because I think he's understood on it.
Yeah, I'm not expert on that either. But the main difference I think between is close and approx is approx gives you better error messages when you test things with PyTest. So that's the major benefit.
There's another comment online from Kyle that there are some GitHub actions that take output from PyTest and format it nicely, including coverage. We use coveralls as an additional action.
Okay.
Thanks, Kyle. Anybody else have a question? All right, it looks like we can go to break 4 minutes early. So we'll be back at 11. And thank you. Thank you.
Are we good to go? Cool. All right. Welcome back, everybody. So the next lecture is about property-based testing, and Deepak will give this guest lecture. Deepak used to work here at NCAR at the oceanography section as a scientist. Now he works at Earthmover. I'm sure he'll talk what they do there, but yeah, it's quite exciting. Deepak is very interested in software correctness, scientific considerations, and reliability. So I'll just give you the chance to talk about these. Yeah.
Yep, thanks. So yeah, my name is Deepak Cherian. I trained as an oceanographer, and then about 2 years ago, I left NCAR to go work at a company called Earthmover. And over the past 2 years, I have really grown to love property testing. And I've tried to, this talk is really about some real world examples of where we found this useful. A case where it really failed, honestly. And then I'm going to try to get you to think about properties and then kind of show you why. Hopefully you'll see, like me, that that's just a lot of fun. And then we have a little notebook bit, so we can try and get some hands-on examples, but honestly an hour is kind of short. And so I'm really going to focus on getting you thinking in this kind of property testing way. So yeah, my name is Deepak Cherian. Today I'm a forward engineer, trained as an oceanographer. Since like 2017-ish, I became pretty actively involved in the scientific Python open source ecosystem. Mostly a package called Xarray. I don't know if, raise your hands if you know Xarray, use Xarray, yeah, awesome. Sorry? Yeah.
All of this.
yeah, I discovered XArray, it made my life so great. And then I said, what is this open source thing? I became very deeply involved and really got trained up as a software engineer on GitHub with a lot of people spending their time mentoring me. 5 years of being a scientist, me, a bunch of other people really became convinced that Earth's system data infrastructure was not built for the 2020s, and there was a lot being left on the table and needed to be done better. And so Ryan Abernathy, an oceanographer, Joe Hammond, who used to be here too in CGD, started this company called Earthmover. And the whole pitch is that we want to build cloud native data infrastructure, and it's for scientific data, specifically understands arrays, and we want to make it a lot more ergonomic to work with weather and climate data in like the 2020s, using the cloud. And it's really important because, as we've seen, there's a lot of private sector interest right now, particularly in these kind of classic data sets that have been research only. And so we think there's just a lot to gain humanity-wise if we can just make the research, private sector, and the nonprofits all talk to each other through these data sets. Oops, I missed a slide. Right. So over the past 18 months, I've basically worked on building property testing suites for a bunch of open source projects. First one is ZAR. ZAR is a data format. Think of it as NetCDF, but more attuned for the cloud object store. It's basically a key value store. You give it, a key and you store a thing, but it looks like an array, so it's very easy to stick any NetCDF-like data in there. ZAR is a data format. This means it cannot lose or misrepresent data. It wouldn't be very useful if it did so, right? So correctness, very important. IceChunk is a technology that we've built. It makes ZAR look more like a database. So it adds this idea of transactions. And so there's a lot of emphasis on safety and correctness, especially in concurrent settings over vanilla ZAR. Again, it's a data format, so you cannot lose or misrepresent data. The stakes are very, very high, so we care about correctness. The past few months, I've worked on a open source library. It's called xpublish tiles, which basically takes data that is stored in ZAR and makes a Slippy web map. So it renders data. The charge for this library is also pretty broad. It's like given basically any data set, coordinates and data stored somehow, we should render a region of the globe. And you have to faithfully represent the data. If you did that wrong, someone's going to think the data set was wrong. It's going to spend a lot of time debugging it, right? So the input space is large. Correctness is also very important. And then a kind of project, personal pet project of mine has been looking at kind of grouped aggregations for arrays, a library called Flux that I built. Grouped aggregations, think of that as comparing things like climatologies and binning and histogramming and stuff like that. Oh, here the input space is also big because you could execute your computation many ways, serial, parallel. You could use a compile library to speed things up or not. There's many array types, many data types. It's just a very, very broad input space. And again, we want correctness, right? And so I've basically been using property testing in all of these libraries for 2 years. So what is property testing? Manish just gave us a quick intro to unit testing, which is where you define your input, you define an expected output, and you compare the two, right? Property testing is a little different. It's a little more abstract. And so that appeals to me with my scientific training. So the idea there is you have some input space for your program, right? And your program or your function is going to take an input sampled from that space and transform it to the output. Instead of testing the exactness of that output, what you assert is a property holds for that output, right? And so my take on this kind of thing is like in a unit test, I am the one that generates complexity, right? I choose these other test cases to test. And so you're kind of always limited, like how much effort did you spend in covering this large input space of your program? And in a sense, like I am the oracle. So I've learned since that there's something known as the oracle problem, which is given an output, how do you know that it's right? And so for a unit test, you are the oracle. You write down, this is the right answer. Make sure you match it, right? On a property test, it's a little different. You describe how you generate the complexity. You describe how to sample the input space. And then you kind of sidestep the oracle problem by just asserting general properties of the output. And so I'm going to show you examples of how this would happen, right? And so you don't really test for specific answers. You test, say, that answer is always positive, for example, if that's a property. And so Usually what this works is you write something called as a test case generator that samples the input space. There are helper libraries out there. These helpers, they tend to be smart. They put a lot of effort into sampling interesting pieces of the space. And so if your program needed a floating point number as an input, the library will check nans and ints very quickly, almost instantaneously, like you have to opt out. If you ask for integers, it will very quickly give you the lowest representable int for that type, the largest possible int for that type, and send it in, right? So you are basically forced to deal with edge cases. They're very, very good at this. They also have, some kind of logic for like sampling the space in the middle. For each test case, you assert that a property holds. And let's say the property doesn't hold. A group property testing library will do something known as shrinking, which is it has heuristics for making a simpler input. How you define simpler is, it's a bit of a heuristic, but the library that we will use, hypothesis, shrinks integers towards zeros. How they do this is very cool. They start twiddling the high bits. And so if you like reduce those to 0, you'll naturally shrink towards 0. Floats also shrink towards 0, right? And so there's two little concepts here. One is the concept of sampling the input space. And the second is the concept of shrinking. And so we're going to spend a lot of effort in the notebook thinking about how these things are generated. And one takeaway should be is that you should always read the API docs to understand how hypothesis is generating inputs and what it shrinks to. The shrinking bit is really, really important. The shrinking bit is important is because it will give you a very, very simple example that can then become a unit test. And it makes it very easy to reproduce. And so the reason I love property testing is I've been working in these situations where the stakes are kind of high. Data formats cannot lose data, right? That's just the given. If you did that, you wouldn't be around for very long. With my kind of for-profit company hat on, we want to move pretty fast and confidently. It doesn't really help us if I'm spending my time distracted by fixing a bug I introduced 3 months ago. And so really, test case coverage is very, very important. And so this kind of generative complexity is very important. With my open source hat on, it's really, somebody expressed this and it's like, that sounds like me. It's like, I'm on the hook if this breaks. And I don't want to be on the hook, right? I want to put it up there and be done. So again, but it's very similar, right? I don't want to come back to a thing that I've already done if I can help it. The input space is large, so for a data format, we have to be able to accept a wide range of inputs, represent it faithfully on disk, and bring it back. It's also true for many, I think, numerical problems or analysis libraries. X-ray is a good example. You can put a lot of things in it, and we have to ensure correctness always. Covering that kind of thing with unit tests is hard. I used to think that we just had to find every bug manually and write a unit test for it, but this is unsustainable. And lastly, this is fun, to me at least. It's more fun to me to write a property test than a unit test. I find these to be very elegant. And honestly, I find them to be like a tool for thinking about the problem because you're forced to think in this very general sense. And if you find a bug, you're kind of forced to step back and think about it in a big picture. It's like, what is the property that's being violated here? Is there one? And like, how would I write it? So I'm gonna talk quickly about how I've used certain examples of properties. We'll do a bit of hands-on exercises in a notebook. Please interrupt if you have questions. I think this would be much better off as an interactive exercise. I have one fail case to show you kind of the dangers of property testing. Not danger, but like the human side of it. It can lead to a lot of overconfidence. And then I'll summarize with a few lessons learned kind of over the last 2 years. So this first little bit is the bit that I think is super fun. It's like, how do you think about properties or choosing properties? And it's kind of flavor of what you would test. There's a lot of information on the internet. I will shout out this one talk, which is the one that really blew my mind. It's by a professor named John Hughes, who is one of the two that pioneered this idea in, I think, like late 90s. So he's been talking about it ever since. This is a pretty recent version of the talk from 2020. It's called How to Specify It. There's a paper, there's this YouTube video. I recommend it highly. It's a very, very good talk. Yes, my favorite quote from the talk is it says, "Do not think, let QuickCheck," which is a property testing library, "do your thinking for you." I find it's really funny, like a professor whose job it is to teach people how to think, tells people to use software to think. But He's got it right though. So you should think at a, different and a more abstract level. So in how to specify it, he lays out some heuristics for thinking about how you would generate properties. And so I'm just going to go one by one and give you concrete examples. The first one is to think about invariance for your problem or your function, or what's called validity testing. Here's an example from this tiles library, which, like I said, takes data and renders it on a globe. So here's the property. For a data set that has global coverage, every pixel should be populated, right? So no subset of the globe that you render to an image should ever have a transparent pixel. I'm assuming an atmospheric field or something, right? So it's not the ocean, that there's land and all that. And so this is a previous version of the software had this bug. That's a seam at the 180, at the anti-meridian, a common problem. Fixing this is hard. And so the property just says that shouldn't happen because this is a data set with global coverage. Like if this is a bug, right? And so one thing to take away, the property is very simple. The complexity is in the input space, right? And so what I do is I take this property and I test it over, well, you can store your data with latitudes increasing or decreasing. Decreasing is common choice in like satellite imagery. You can store longitude values with different conventions. So you could go -180 to 180, you could go 0 to 360. Either way, you need to handle the 0 and the 180 properly. You have to be able to do that for arbitrary data shapes, arbitrary grid resolutions, etc. And it's a slippy map, so you can zoom in and out just like Google Maps, and this property has to hold at any arbitrary zoom level, right? So the test space is huge, and I could write unit tests for each of these, but it's never going to be complete, right? And so instead, what we use this library called Hypothesis to sample from that input space, just generate data sets for me. I'm going to render a tile. I don't really care what that tile looks like, except that it has no transparent pixel, right? And so that fixes, really tests for that one specific bug. But it kind of illustrates this point where you think in generalities. You don't really care that there's a sine wave in this tile. You could try that too. But the property is very, very simple. There's like no transparency. Example from ZAR, which is more of a data format. The very simple property, it's just a round trip test. We read what we wrote, right? Like what you have in memory gets written to disk, comes back. The space is huge though. Arbitrary data types, ints, floats, characters, datetimes, etc. Arbitrary data shapes, arbitrary dimensionality, like 0 to 32 or 64. Arbitrary data actually that's being written, right? So there's lots of complexity there. With ZAR specifically, you could write to an in-memory store, an object store. You could write it to file storage. There's all of these places you could write it. You could write to a database, to a zip file. But like that round trip property must hold, right? Otherwise, it wouldn't be a very useful data format. And so we test over this. We test right to, given a prefix, we write to arbitrary file paths within there, arbitrarily compressed to some level. Arbitrary chunking, so similar to the netsieve idea, an array is cut up into chunks when they're compressed and then written to disk. And so you can vary those chunking strategies. And then a lot more. We support arbitrary attributes. And so you could test, like, we draw from the space of Unicode characters to write, But again, the property is very simple. It's like what was in memory was written to disk, must come back as the same thing. So simple property, large input space. We just assert it for all of them. Okay, this is exercise for the room. We've been thinking about the heat equation. So you have it discretized here in these 3 cells. What are simple invariants that you could test in general for this system? I'm gonna raise your hand, shout it out. The heat equation, guys, what's the invariant? Yeah. So conservation of heat, maybe, right? So if you have insulated boundaries, there's no source of heat, it just stays, integrated within that volume, it stays constant, right? Simple property, it's generally a simple setup, but you could test it over arbitrary initial conditions. Anything else? No new extrema. Yeah, great one. No new extrema. So that's a property of the equation. So if you have a maximum value, your solution must always be less than or equal to that, right? So simple invariant, you could do it over arbitrary things and really test. And so for this kind of thing, a really good place to look at is just the mathematics of the problem. They tell you what those invariants are, right? There's one more on this list. I forgot what it was. Someone remembers, or wants to throw it out? Symmetry preservation. So I think Alper introduced this one. So yeah, if you start with symmetry, you must end with symmetry. And so as long as you generate those initial conditions and those boundary conditions, you should be good. And so we'll work on how you go from that statement on the board to like actual code and just kind of look at what that looks like. But for now, I'm just going to move on to a different heuristic for thinking about the problem. That was invariance. Next is to ask, what is the post condition? Are you, because remember, you're kind of randomly sampling the input space, right? So you can't write an exact output in general, but maybe you can construct inputs whose output is easy to predict. So this is an example from like a group by problem, right? So let's say I have an array A and I'm grouping by an array B. But if that array B was all constant, there's only one group. And so it's equivalent to just aggregating the array A. Here's a concrete example. So let's say I start with array 0, 1, 2. I'm grouping by an array of arbitrary data type, but constant values, right? So it could be 1, 1, 1 or AAA. And so A group by mean is identical to A dot mean. There's only one group. They all belong to the same. It's all the same, right? So in this case, I'm basically using, NumPy or a different library to generate the mean. You could think of, if I know what the constant is, then the mean of that is just the, if I initialized A to say 1, 1, 1, the mean is going to be 1, right? So that's another way of constructing an easy output. So relatively simple property, A group by mean is identical to A dot mean for this case of B's, which are all constants. But if you do this, you start testing handlings of infinities, nans across all data types. With NumPy, you have to worry about things like D-type casting rules and stuff like that. So again, simple property, complicated input space, gets you a lot. So again, exercise for the room. So let's say, what is an input whose output is easy to predict with the heat equation? The hint is we actually, like, one of the unit tests tested that. Constants, exactly. If you stick U equals constant, nothing happens, right? And so you can test that. Anything else? Yeah. Monotonicity is one. You could even do things like if I only, oh, Sam. Yep. Telescoping. It's a little hard to predict a specific output, yeah. But anyway, it's things like this, right? So yeah, you can, the solution is invariant to arbitrary constant at least. And so you could just add arbitrary constants in there to a solution and you should get the same thing. You can start testing things like that. And then if the boundary fluxes are heating, then temperature's got to go up. If the net boundary flux is cooling, then temperature's got to go down. Right? So that's an easy output to predict. The third one, and to me, this is the most fascinating one. Yep.
Thinking about it. So you're just asserting that if you're adding heating, it's going to go up.
Yep.
Not testing exactly how much goes up.
Exactly.
Just the property.
Yep. Yep.
Whatever.
Okay. So the next one is called a metamorphic test. And this one's, I find super cool because in some sense, invariance kind of tests properties of the problem. So, there's a lot of complexity there. The previous one, we constructed a test case where the output is very simple, right? And easy to predict. This one just says, we're going to deal with all the complexity, but say that related calls yield related results. And so there's kind of a famous example from Spotify, which is the property is if you search for the phrase word 1, word 2, you should have fewer results than a search for just word 1. Right? So adding more search phrases reduce number of results. Yeah, that was a bug for a long time. But again, like very simple statements can be very effective, right? And yeah, there's a paper. I have a citation. You can go and read it about things like this, about metamorphic testing, right? So again, you don't say word 1 must give me these 10 results. You say that word 1, word 2 should be less than word 1. right? So it's a property. And you can test it with the full complexity of your song database or whatever. You don't have to create a simple database to test it. One that I used in my little group by library was that forward filling and backward filling are inverse operations, like in directionality. And so here's forward fill. So it's I started with 1, 2, nan, and 3. Forward filling that means the nan gets replaced by 2. Backward filling that means the nan gets replaced by 3, right? So you fill this way, you fill backwards. But there's directionality here, right? So you can flip them. So the forward fill of A should be identical to the backward fill of the reversed A. And the backward fill of A should be the forward fill of reversed A, right? And so you can play games like this. And so the cool thing is you can test this now over a whole space of inputs. You never predict an exact output. You just assert that your two functions are really inverses of each other, right? Super effective. You can find this kind of property in many places. A thing that may be more interesting to people in this room. So again, this is from my plotting library, which you could think of as a regridding problem in a sense, right? You're regridding data to the output grid, pixel grid. There's many ways of specifying data on a uniformly spaced grid. The first one on the left down here is what's called the geotransform. This is very common in geospatial satellite imagery, raster imagery fields. Basically, it's 6 numbers and a shape. So it specifies an affine transform. It gives you an origin and a spacing, and that defines a uniform grid along with the shape. You could do it a way that we would do this in this building is you would have a rectilinear mesh, right? So you'd have 2 orthogonal coordinates, x and y for a 2x2. Or you could think of this as a curvilinear mesh where the x and y's are now 2-dimensional coordinates, right? So the more general case. All of these are 3 different ways of specifying the same information. It's the same grid, it's the same data. So the output should always be the same. But in reality, it ends up testing 3 different code paths in my library, right? And so the property is like the same data gives you the same image, and it doesn't matter how the underlying coordinates are specified. And like you can go all 3 ways, right? And so this is again a metamorphic test. Like the actual values, the actual image doesn't matter. We just assert that it's the same no matter how it's specified. I think metamorphic tests are super useful for sciencey things in a way. That's what like most mathematical analysis does. So yeah, heat equation, boundary conditions, what kind of related calls yield related outputs. Like what would you do?
The U array, let's see.
The output should be reversed, right?
Yeah, it should be reversed.
Yeah, that's fine. There's symmetry about the center, right? So if you flip the problem, change your fluxes, you get that. Yeah, good one. Symmetry about the center. This one. Shifting the x invariant of shift in x. This one. This is assuming that you were working with like concrete x values, for example. Just offset the x coordinate by 100. Doesn't matter. Same. Arbitrary constant to the initial condition. Well, the solution must be unchanged, but as long as you undo the transformation. The last one I thought was maybe interesting. So let's say you have a solution for delta t, delta x, and should be approximately equal to that, but scaled down. Right? So delta t over n, using a smaller time step to like numerics should get you a very similar answer. Curious what people think about that. The other thing is also, when you analyze this kind of system, you always look at non-dimensional parameters, right? And so the kind of physics tells you that the solutions are similar. And so you can try to start generating solutions and then assert that those are similar depending on the non-dimensionalization, right? So I think that's probably pretty effective property. The last one is what are known as model-based properties. So this again, going back to the Oracle problem, the metamorphic test just kind of ignores it completely. You kind of be clever and you sidestep it. In this one, you implement a simple Oracle. And this only really works if the model is simpler to implement. One example where we've done this in ZAR is I have a NumPy array and I index it this way, so I extract some some values out of it, it should be identical to indexing the ZAR array the same way. But in this case, we implemented these operations for the ZAR array, and we rely on NumPy to be correct, right? So someone else has done it. And so that's a model for my array, and I just keep testing against it, right? And it really works because by definition, the ZAR array semantics match NumPy. So that's a property that I'm testing in this way. We do more complicated versions of this. If you have time, I can demonstrate. I couldn't think of a simpler model for the heat equation. Like, how do you simplify that even more? But you could do it the other way. That heat equation solver could be a model for a more complicated thing. For example, ocean model vertical mixing scheme. You got fluxes. If you heat it, it's got to heat, right? And so you might ask, is there a more complicated system I work with that in some limit should look like a simpler model, a simpler equation that is easier to implement? And you can test against it. Alper. Yeah, something the complicated things. Yeah. Yeah. The model-based testing, if it's very important that the model should be easier to implement, right? If you have a bug in your model, it's not going to help you very much. But if you can find a model, it can be very, very effective. The kind of canonical example is where people test distributed databases against a very simple in-memory database like a dictionary. And so, your distributed system is like ensuring consistency all over the place, and it's all kind of complicated, but the dictionary is very easy. It's like input, output, input, output. So testing against that, super effective. It's a technique we use. Okay, so yeah, it's about 30 minutes. We're going to jump to a notebook. Credit to Alper for writing nearly all of the notebook. So we're going to look at similar tests and kind of explore this library, a Python library called Hypothesis. Hypothesis is a very, very good property testing library. It's estimated to be used by like 5% of Python developers, which is a huge number. It is very opinionated. You will see that, but like I really admire them because they're very focused on user experience. They're focused on just making it very easy for anyone to write a property test of some sort, and they make lots of choices to make that very easy. And they try to add a lot of heuristics to give you like good problem space coverage and stuff like that. It's super open source. The most famous property testing library, the original one, is called QuickCheck. That one has some proprietary. But Hypothesis is open source, is integrated with PyTest. So this stuff can live right next to all your unit tests. It works very well. The documentation is very good. You should be reading it a lot if you're kind of going to go down this road. There's a lot of teaching that happens in that docs. They're very good at communicating concepts in addition to just like API reference. They release really quickly. They release like every day or two. So it's like, this stuff is constantly moving. And they have lots of helpers for easily integrating with continuous integration suite. So we use that a lot too. All right. Okay. So if you click over to this notebook, I've scrolled down a bit to this hypothesis section. Actually, maybe before we do that, does anyone have any questions around the idea of property testing or how you think about these things? Or
well, yeah, Deepak, I'm just curious, when do you, just from your last slide, when do you decide when do you decide to use a property test versus a unit test when you're testing your own code?
You should do both.
Always do both. The property test is, to me, it like generates complexity. It like explores space and almost always finds things that I didn't think to either test or I didn't realize were invalid inputs, and now I need to like. And so one of the things I've kind of learned is a good property testing suite is like an empirical specification for your program. It's like, I do not accept nans, because otherwise it would fail. And so do both is the answer there. Sam?
Explain a little bit more the difference between an invariant and a postcondition.
Yeah. I will say that these heuristics they kind of blur together, honestly. Specifically with the metamorphic tests. But I think the idea behind an invariant is that invariant and the postcondition. So the postcondition is where you basically have a specific output that you can construct. And invariant just says the output, satisfies conservation of heat. So the integral of the solution has this total heat content. What is the post condition would be a constant field does not change, right? So I guess that's also an invariant, but you can also write out that the output is a constant, right? The constant that you stuck in. So in general, it's that the post condition stuff is what the output is easy to predict, and you can construct it. Ooh. Actually, I can read that out. An invariant is a property that holds true before a condition and after it as well. A post condition only needs to hold afterwards and is often dependent on the particular input. Okay, yeah, that's a good way to put it.
Just to add to that, invariant could be more granular too. Like you can have loop invariant, where you expect some property to hold at every time step of a loop.
Yeah. Since I don't have any follow training in this, so I learned a lot also. One thing I have found, like, you could start with one property and then express it like 4 different ways. Is there a good method to automatically translate property testing failures into unit tests? There's no automated way, but Hypothesis makes this very easy. They will print out all the information that is needed, and there's something known as an example decorator that you can do. So I'll try and remember to show that once we go to the notebook. Or maybe I can do it now. Yeah. This is the thing to think about, but we're going to get into this now. But here's a test function. It gets an input that could be arbitrary strings, and these are specific strings that will always be tested. So that's a unit test and a property test in one. So if you find a failure and you want it to be always tested, you could stick that example in there and we'll run it. Yep. Okay, so we'll dive a little more into that kind of syntax now. So here we're starting with this division function that we've been working with. Just kind of reduce how much errors it spit to screen. So yeah, so usually, here's a function that you start with, and you've been very good. You wrote the precondition, the implementation, and the postcondition, right? And now we need to test it. You can make, so I guess this is the postcondition failed. And so in this case, Alper wrote out this case, 7/25, that cannot be represented exactly in floating point. And so we caught a failure. But there was a lot of magic there. How did you think to test 7 and 25, right? And you kind of illustrate this point down below is that you could test a bunch of random numbers like that, and all of those end up succeeding, right? And so here's a bunch of unit tests. They are testing your code, but they're not very good at finding that one case, right? And so we're going to try and rewrite that test as a hypothesis test. And so I'm just going to talk through the kind of syntax of how you do that. So here's your test function. It takes 2 inputs, x and y. And it's like, what are my inputs here? I'm going to start by saying, hey, give me a value drawn from the space of integers, and give me another value drawn from the space of integers. So these are 2 independent draws from the space of integers that will be provided to this function. I'm going to assume means I'm going to reject the case where y, or like assume that y is not equal to 0, right? So the denominator cannot be 0, division is undefined. And so I'm going to reject that particular case if that ends up coming in. And then for everything else, I'm just going to assert that the division succeeds. All right, so what happens when we run this? Oop, I didn't actually run it. What I'm going to do is run it here. Oh, one thing I wanted to find out is in this lecture, we're just going to be working in a notebook because it's pretty convenient. But all of this stuff you can run through PyTest. So there's a command line invocation that you can type out that will run it. And actually, when Manish did it, he saw the little test metamorphic.py is a bunch of property tests I added as an example, and those kind of ran just when you run PyTest. So it's all very integrated. But for now, the code is all in a notebook just because it's easy to type and modify. One thing I'm going to change is also I'm going to print X and Y, so you kind of see what's happening, right? So I'm going to run this. Oh, look at that. So very large integer, small integer. We tried negative integers. Oh, look, we tried 0 and 1, 1, 1. Very, very, very large numbers. It just keeps going. And oops, there you go. Falsifying example, 1 and y equals that. What's the probability you would have written that down? Right. But it's kind of cool. And it found x equals 1. This is what I said, the integers shrink towards 0. So the kind of smallest, presumably the x equals 0 passes. And so it's found like the smallest numerator that you could find. You can kind of see here, for example, like this number ends up getting repeated. So it found 1 in that, it tried 0 and slightly different numbers. Then it tries a bunch with 1 and then it comes back to this. And so there's a lot of technology that's hiding under all that syntax. Right? All you did was say, hey, give me something from the integer strategy. And that integer strategy is kind of has some heuristics for how it explores this space. And it's very random. Well, somewhat pseudo-random, right? It's still like trying to shrink when it finds something that fails. It tries to test interesting numbers. I bet you will find things that are close to integer max and int min somewhere in here. But yeah. But this is a property test, right? You have asserted nothing about the output except that except in this post condition. So you're not looking for specific values, right? You're asserting this relation. And you've tested that relation over a very wide range of numbers, more than you would think of doing. And every time you run it, you will get, slightly different. Hypothesis, like I said, is very, very smart. It makes it very easy for you. Once it detects a failure, it will write it to a database. And the next time you run it, it will rerun that failure pretty early on. So that's what's happened here, right? It's just retried the thing. We're like, nope, you still fail, right? So it is random search, but it helps you fix the bug, right? Ooh, thanks.
Treat the test function as a black box, or does it use EG coverage to get inputs that activate different codes?
I think by default, Hypothesis treats it as a black box, but I'm pretty sure there's a plugin or an extension that tries to do the code coverage stuff. Like the Hypothesis ecosystem is like growing, and they like plug it into all kinds of other testing approaches. So you can do a lot with it. Yep.
It's true function. Is it possible to name those?
Yeah,
Do they
yeah.
match your names of your inputs? It
Absolutely.
seems like, because right now it just is basing it off ordering.
Yes, correct. So you can always do named parts to that decorator, and it's fine. So you could say X is drawn from the space of integers, Y is drawn from the space of integers. Pass that into X and Y appropriately. I added test div property, which is actually down below here too. So if you run that, you should see it. Yeah, sorry about that. It's got to keep it interactive though. Yeah.
Leave the print statement out. It gives a return that gives you. Yeah.
Yeah.
What's up with that?
So one of the ways, this is where Hypothesis is very opinionated. You've basically invalidated the cache because you've changed the body of the function. And so now it's like explored somewhere else and it's come with a different, simpler example of 45 thirdness. So now you're seeing some of these, the randomness working. And yeah, if I repeat this, it will keep changing. I don't know, let's see. This is a useless statement, but now it's gone somewhere else. Okay, questions?
Maybe you're going to address this later, and if so, we're to punt on it. But that's so I'm really loving a lot of the things here. But the randomness piece is making me a little uncomfortable, just because like in doing regular unit tests that aren't property based tests, I've definitely run into problems where like we have some trying to test across a random space, and then like everything's passing for 3 months, and then suddenly our test is failing because it happened to find that one random thing that caused the test to fail.
Yeah,
and that's really problematic. I'm curious what your kind of experience is here. I mean, partly this is addressed, it seems like, by writing the failing thing to a database. So that addresses it on the backside of how do you reproduce it after the fact? But there's also the like, are you gonna stumble across the thing that, and how many tries do you need to stumble across the failing thing? What's your experience with that?
No good answer here. It's pseudo random search. It does not prove anything. It's not exhaustive, right? And so the one thing I want you to take away from this session is that you should think a lot about what's being tested. And I have a concrete example, but I was very overconfident, introduced a very bad bug. And then I looked at why did the property test not catch it? It's like, oh, I'm off exploring this side of the space that is irrelevant for this function. Like I'm exploring, complexity of attributes and stuff. I should have been looking at this other thing, right? And so no good answer. Observability is a bit of a problem. Hypothesis is working on that, like try to like visualize the input space and what you've covered. I haven't actually learned any of this stuff. I would recommend, I recommend reading the docs. Yeah, this Tyche thing is like a VS Code extension for observability. So it lets you like look and see what's actually being exposed. You can always print pretty verbose output to screen. I can show you that. But then you're relying on your eyes catching patterns. Honestly, no good answer. It's random search. They try to help you with the database and like you can run it by like reducing the randomness. So like in CI, you may want that. So like, yeah, I can talk about this more about how we do it in CI, but nightly we run with randomness, random search over 10,000 examples. On every PR, we run non-random search. So you really repeat the same thing as much as you can, but only 100 examples. And so you can play these games. Mike. Like the random search gives you a problem. Is your inclination like go back through all the versions? Yeah. A long-standing bug that just happened to be caught, or yeah. So you can do bisection. Once you have that, you can run the example like this way. Like I said, you'd have to import example, but you could see. So for example, this addresses the previous question of how easy it is to reproduce. In theory, this should come back again. That should be the first one it tried. So this just makes it a unit test now. For more complicated things, they have a decorator that's called reproduce_failure. And you will enter like some random characters. It basically seeds their random number generators, so you generate the same steps. So like I said, Hypothesis is a very good library. It does the random thing, but it helps you get to like deterministic failures. There's questions back there? Yeah.
Is there a way that you can like control the seeding for the pseudo-random number generation?
I think
in order to reproduce a test?
I think you can, but I think, see, this is where I say Hypothesis is very opinionated. And it's one of the complaints people can sometimes have, and I do too. It can test the simple case a lot, and like, I don't necessarily want the simple case all the time, right? I want like some minimal complexity. That's the thing you hammer. And this will come into my story of a failure, basically. It's like you have to be a little more careful. And there, like I said, there's also stuff that I don't know as well. You can tie into like a fuzzer and other different tools that are, and then kind of you orchestrate them to Hypothesis. There's a lot here that I don't know, honestly. But yeah, the idea behind Hypothesis is to make a lot of complicated technology very easy to use, right? And so my recommendation would be don't get too hung up on this kind of thing. Like definitely think about what you're generating and like what part of problem space you're sampling. The properties that you're testing are usually very, very simple. And you want to spend the effort thinking about like interesting inputs. Like there. Yeah.
Or say which part of integers
the
random generator generates examples.
Yep, I will show you that. Yeah, assume is a pretty blunt hammer. It's good because you could do like very complicated stuff, but there's better ways. I will show you an example here now from the czar. So in the czar spec, there are these requirements. A name for an array or a node, a group and an array, cannot be the empty string, cannot include the character slash, cannot be a string only of period characters, and cannot start with double underscore. These are rules. And so I wrote a hypothesis strategy. We sample from this set of characters. I build text min size 1, so you cannot have the empty string. So that's how we've limited the space that was sampled. So there's no assume here. I just told it. And it's it's basically always better. You just tell it, never generate 0. And then I have these somewhat complicated conditions so that I can chain in a filter which says, hey, not dot, 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 or starts with double underscore. And then I also filter, there's this other requirement, turns out not in the spec, found empirically that we have to exclude this special name. Reading this last night, I realized there's a bug here. We only exclude dot and dot dot. The spec excludes dot 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 also. but anyway, this is how you start with simple things and you chain things to get complicated things. So.
Is it possible to, I guess, probably. So like if you have this constraint and like the user can't give you a dot or a dot dot, it doesn't start with double underscore. To reuse that filter both here in your test as well as in your actual in the code.
Yeah. This is why, like, this is to me empirical spec here, right? It's in the code and it's tested, and it's independent of the actual spec writing of the actual code. It's like the third one, and so doing this, yeah. So the reason the czar JSON thing came up was that there was a test that started acting weirdly, and we dug into it and it's like, oh, this is the problem. But it's also a thing that would rarely come up like randomly generating that sequence of characters is kind of rare, right? But it's in there now, so it's like an empirical specification for what we accept. Okay. We're kind of moving a bit slowly, but that's okay. Goal here is to show off hypothesis. So I hope I've shown you some level of shrinking, right? We had a failure that had only 2-digit numbers. We had another failure where the numerator was 1, but not 0. So hypothesis is good at this. It's got heuristics for doing it. You don't necessarily have to think too hard about it. This is honestly maybe the most important bit of this lecture is you need to think about what's being generated. And hypothesis comes with a lot of helpers to let you combine things. So they write strategies for generating base things like floats, integers, numpy arrays. And a lot of times you will take these strategies and then compose them to make more complicated things, right? So here's one. Alper wrote the strategy. It's like we want to sample from the space of integers and floats. And so there's a helper function, one-off, which will pick from either integers or floats. For floats, I control the input space by saying, hey, I don't like nans, I don't like infinities. You can even turn off subnormals if you wanted. And there's usually a lot more. So if you're writing, you should have the API reference up so you can see what you can control and what parts of the space it samples. The second thing you need to think about is shrinking, right? And so if you look at the docstring for one-off, it will tell you that it shrinks so that the earlier strategy is considered simpler. So if it finds a floating point failure, it will try to find the integer failure. And then if it doesn't succeed, it will go back to floats, right? And so shrinking behavior is important to think about. By putting this order in here, you've said that I prefer integers as a simpler example to floats. This may not be what you want, and it's something you should think about. Like, but stuff like this really matters. I commonly generate strategies in a notebook, and you can call dot, oops, and run it. You can call dot example to get you a sample draw. So that was the first one. I can just keep running this. You can kind of see it's getting float, 0, float, integer, float, negative integer, 0. So you can kind of build your strategies in a little notebook, do this interactive exploration, make sure it looks like what you like, and then you shift it off to your code base. And then once you have that kind of strategy, you can use it with the given as usual. So now it's found a different one. And it found integers, simpler, right? All right. Okay, so one-off is just one of them. There's a lot more. There's builds, which lets you construct custom objects. There's sampled from, which is one I just showed off here. It says, hey, sample from this list. And characters that appear at the beginning are considered simpler or are tested more frequently. So again, once you start using this a bunch, you start remembering the shrinking behavior and you kind of think about it. One of the things I don't like about this strategy is you might want to permute this a bit so that the special characters come first. You test a mix of numbers and capitals and lowercase all in the beginning. So you're kind of hammering that space. But any property test is better than no property test. So just start simple, go from there. Just as useful, yielding just one value. I showed you an example of how you can use filter. There's also a map, so you can transform a thing you've drawn. Composite is a pretty more advanced case. There's an example at the end. I'm not sure we'll get to it, but I might try and talk through it. I will skip this section. Hypothesis gives you a lot of control. There are a lot of settings, controls output, a number of examples run, et cetera, et cetera. It's a very good library. We'll go back to the heat equation solver for about the next 10 minutes. And we'll look at testing some invariants. And yeah, credit to Alper for writing really all of this bit. Oh, I wish I put the equation up there. So this is usually what using a hypothesis looks like. Is you first start off by writing a bunch of strategies, right? And so the first strategy we write is a strategy to generate floats. And this is just in general, it's going to be used for generating the initial condition. So I'm going to say, coming back to the question, how do you control the space? Generate floats between -1000 and a +1000. Nans and infinities are not allowed. Those are not valid inputs to my program. For the diffusivity kappa, we'll sample positive values between 10 - 4 and a maximum value of 10. No nans or infinities allowed. For the delta x, again, we'll do positive floats, 10 - 3 to 10, again, no nans or infinities, and similarly for delta t. So these are strategies, and you're going to draw from them for each of those parameters. For mesh sizes, we'll say we'll choose between 3 and 40. There's some level of arbitrariness here, right? And so you do want to think about how much of the space you sample. Like, is there value to sampling a mesh of 10,000 versus 40? Probably not. Like, so you want to it's a bit like Goldilocks. Right? It's got to be big enough to be useful, but small enough to be easy to explore. These are fluxes, I think, are used for generating boundary conditions. So we go between -100 and 100. But the actual boundary condition is going to be drawn as a 2-element tuple, left and right. And so this is cool because it takes a strategy to define a single flux, and it uses a tuple strategy to draw once and then a second time from the fluxes strategy, right? That may have been confusing, so let's just call, whoops, I forgot to run. I'm going to run. You see, you've got 2-element floats being generated. And so tuples is a strategy that takes strategies as inputs. And so it samples from them, creates a tuple, and then sends it back, right? And so you can do, whoops, I'm going to just keep running the same thing, right? So you keep drawing 2 floats from that space. And so the first thing we'll try is the telescoping property. So it's basically what goes out one cell must come in the next cell so you don't lose anything at the interface. Here's a programmatic explanation of that. You take in 2 vectors, one the divergence, one's the flux. You sum up the whole thing, and you should get convergence, or it should match up, right? And so this is a function that is given the inputs asserts that it doesn't assert, it returns true or false if a property is satisfied. And we're going to put that into hypothesis. So this first example is going to be, I'm going to ask you to use that divergence function to fill in the blanks here and then run the property test. I've written out the generator. So this is a telescoping property. I'm going to take a state as input. we're going to calculate the divergence function. That's the function being tested. And then we're going to assert that the divergence calculated matches the telescoping property. And the input state is just going to be a list of floats between 4 and 21 elements long. And we kind of draw the dx from the dx strategy. So I'll wait about 2 minutes, just write out a call to that divergence function that's in the heat1d library. So heat1d.divergence, that will give you div f, and then you have to assert the telescoping property is satisfied, and then you can uncomment this line to run the test. I'll wait 2 minutes, and happy to take any questions in the meantime. Here's the signature of divergence if you need it. So there's a question in the chat. Even if you run 1 million random tests, you're still checking a finite sample of an infinite sample space. That's right. If it says it didn't find a counterexample, what it actually means is it didn't find a counterexample in that sample, like a guided lottery system. Yes, exactly. A successful property test run does not prove anything about your program. It just means that it didn't find it. So it's very empirical, I guess I put it that way. And it's also why I keep emphasizing you need to think about what's being generated and make sure that sampling the space in a nice enough way or in a useful way. Question?
I have an example in mind. So if this sounds kind of specific, it is. So I have a code where there might be cases where I want to test properties on like an arbitrary grid. I've got like 2 different classes that represent different types of grid. And one takes like some set of parameters about the domain size and resolution. And the other one takes like an arbitrary non-uniform grid, like a lot more parameters. So is this like, can you build up by just chaining together all of these things that you could generate an arbitrary either of those? Like with the one of, you could pick which grid you wanted or something?
Yes, yes, but you still have to write a strategy that generates one of those grids. And that gets, it's inevitable that you will want to write a more complicated strategy. And there's an example. Unfortunately, I don't think we have time to look at it, but there's this thing called composite. And composite is basically the escape hatch for writing anything as complicated as you wanted. Okay. And so I'll try and cover that quickly. I can show you examples. Like ZAR, for example, provides a public API. Like we've written strategies and you can use that in your own testing. And so a lot of them are these composite things, and like we give you a lot of ability to control it. Okay, I'm going to try and write this out now. Let's see, so div f, I'm going to initialize an array. What was it? Line f, and then heat1d.divergence. Did anyone manage to get this thing to work? Yeah? Did it succeed? Nice. Alper is very good at writing code. That's it. Sorry? Printing nothing is success, yes. Ooh. Sorry, that was, could have sworn I ran these cells. All right. Okay, what did I do wrong? Aha. Look at that. Oh, sorry, I've been really bad about running cells. All right, try it again. Oh, no, it worked. It's really fun to actually try and make it fail. So I'm going to try that. Let's see. If ln f mod 2 equals 0. Let's do. So that could be 0, 1. So this is clearly very bad. Let's see what happens. Oh, no, did it just not? Okay. Python import problems, but yeah, I'm gonna skip that for now. It's really good if you're writing a property test that you actually make sure that it fails. Yeah, like it has to catch something. You gotta be careful. Yeah, same stuff that you do with unit tests. Just do the same thing. What's the time? Okay, it's about noon. We have 20 more minutes. Yeah, let's spend a couple of minutes trying to write out the conservation property. In this case, I've given you the answer for the core of the test. Well, Alper has. But what I want you to do is write the given statements. So, write out the generator. You can look up for hints and then run that down here. And I'll wait about 3 minutes. So just to make sure, right, I can copy. And we should be doing something like u old equals something, kappa equals something, dt equals something. Did everyone succeed? We're working. Can wait a couple more minutes. Got some nods. Great. All right, so we have about 12 minutes, so I'll move on. This is the answer, right? And so it's pretty common to write these strategies in one place, like a specific submodule called strategies, and then you kind of reuse those all over the place. So we draw from the kappa, dt, dx, and bc. Those are all defined earlier. The point of this exercise was to get you to write this up. It says generate initial conditions that are lists with elements drawn from the float strategy defined earlier, size between 4 and 21. And then you can see it's like varying everything. The list strategy is going to shrink. So the shrinking for the values of the list strategy is the shrinking behavior of the float strategy. So it's going to be towards 0. And then the size of the list, a smaller list is simpler than the bigger list, right? So this is how it helps you get to a simpler unit test. It's what shrinking does to me. Like it's trying to get you to the simplest possible unit test. All right. Lots of printouts, so hypothesis tried a lot. If you scroll down, there's going to be the symmetry one property, the monotonicity property. I encourage you to read through those. They're well written, and they kind of illustrate very interesting things. The one thing I'm going to hammer on is, this. Because we talked about exploring input space a lot, right? And there was a lot of concern about random exploration. These assume statements are a bit problematic in that sense, right? Because we need a specific stability condition to be satisfied, but we're drawing all of those elements independently. kappa is sampled from one distribution, dt is independently sampled, dx is independently sampled. What's the probability the combination of all of that is going to satisfy the stability condition? It's going to be kind of small, right? Depending on how the space is. This is in like real life usage, this is very common. Like you rarely want independent draws for multiple parameters. There's some relation, there's some part of parameter space you would want to test. For a numerical model, you're guaranteed that everyone's going to try and run it pretty close to the stability boundary. So maybe that's what you want to do, right? You don't want to be like the tiniest possible time step. And so inevitably you will get to writing your own strategy that's a little more complicated. And a lot of time is this complicated strategy is like you will want to make data dependent decisions. So you want to draw, look at those values, and then make choices. There are two different ways. One is with given, there is a special data strategy. And what the data does is you can draw a specific instance from that distribution. So in this case, there was a non-decreasing list strategy. It doesn't matter the details, but like when you draw it, you get a list. And now you can make decisions. So in this case, what I did is I'm going to test monotonicity. I receive n, dx, and kappa. These are independently drawn. dt, not drawn. And so for n, I generate an initial condition of size n, a specific one, that's u naught. dt, I define a min value, and I'm going to say the max value is determined by my stability condition. So now I have specific values, I can make data-dependent choices. And what this does is it means every draw is now useful. Like I'm always satisfied my stability condition by definition, and I'm exploring useful bits of parameter space. So this makes your test faster, one, but it's also how you control the space better. You can like if it was me, I would go between 0.4 and 0.49, the boundary, because that's where I know I will be running my numerical solution, and I want my properties to be satisfied there. The assume statement is now an assert statement. So it's like, be sure this is like, I'm testing my strategy, that I'm doing it right. And then you step your heatification forward, you assert your property, right? So that's one way. There's this data object that you can get in and you can call a draw. You can write a more complicated generator. So this goes to the question about generating a mesh. So in this case, I called it meshes. A composite strategy is also known as a higher order strategy. It's a strategy that takes strategies as inputs. And so in this case, this is just hypothesis syntax. I write a meshes strategy. Draw is required, and you'll see why. And this strategy lets you control the kappas. So you give it the distribution for kappa, for dt, for dx, and n. And so it's going to draw the kappa, it's going to draw a dx, and then it's going to draw a dt from that distribution, but set the max value on that distribution, right? And then it's going to assert the post condition to make sure the draw was valid, and it's going to return a kappa, a dt, and a mesh. So everything you need to like step your solution, except for the initial condition. That's independent now. We're kind of out of time, but like the point I want to make here is inevitably, as was mentioned, you're going to want to do a more complicated generation, and hypothesis gives you the tools to do so. And it's very important, you can make the data dependent decisions. So you get to choose, these are independent draws, and now the dependent ones, you get to work with exact values and kind of make choices thereon. And it's basically inevitable that you will get there. We're low on time, but that's okay. There's a function here, a test file here called test metamorphic. So this goes into writing out some metamorphic properties. There's many ways to write them, but here I wrote the symmetry about center property last night. So it's like you take this system and then you flip it, so it becomes this system, and then you assert that the solutions are mirror images. And I've time stepped it forward like 10 steps. Yeah, thanks. So there's a lot of material in here, but I wanted to show you is that here are concrete examples of how you would write these things, right? So we talked about this property, you guys came up with it, and so here's how it looks like in code. Importantly, for doing the symmetry, you need odd numbers, odd number meshes. And so here I used the composite meshes strategy that I just showed you, but I control the distribution for ends. I always make it an odd number. So this is like complicated stuff happening here. Like composite is very, very good. And it's a really big escape hatch, and you can start to configure your strategies to do useful things. And again, this is important because A, it makes every test run useful. Like you're always generating a useful test. So it's faster. And it also lets you control what's interesting about the space. Like, so you have to think about what's being tested. So that's metamorphic testing. Got no time, but there's something known as stateful testing, which is what really pushed me down this path of property testing. It's basically a variant of model-based testing that hypothesis makes very easy to run. So this is the case where we have a distributed system and we test it against an in-memory dictionary. And yeah, we could talk about it later, but you basically write out, here are all the operations a user of this library can make. They can add an array, they can add a group, they can delete a group, they can create a branch, they can go back. You define all of the options that could be taken and it just randomly generates a sequence. And so the way I think about that, it's like the infinite monkeys typing out a sequence of operations all the time. And like, regardless of what they do, your state has to satisfy invariance. It has to be consistent. And so it's very, very powerful. Right, I kept mentioning this. So here's the bug I introduced. So property testing can lead to overconfidence. This is in ZAR Python. I made a complex change to improve performance. I added unit tests. I did all the good things. The correct test suite passed. I thought the property test coverage was good, but then a user reported data loss. And the kind of detail that's important is ZAR cuts an array into chunks, but the last chunk size can be smaller. So a 5-element array could be cut up into chunks of 2, and then 1. And so the last one can be smaller. And I introduced bug when you overwrite the last chunk and it's smaller. All right. And I tore my hair. I was like, how is this possible? I thought we had property tests, right? Turns out, I did all the print statements and I figured out that we were spending a lot of time testing arrays of shape 0 and 1, which is not very common in real life, right? And then we were testing things like complicated Unicode attributes and stuff like this, but it didn't matter. I was rewriting values, right, in that test. And so we spent almost no effort testing the most common complex case, which is something like this, 2, 2, and 1. And so here's my comment from there. It was like earlier this year, I updated the strategies to be more useful. We test odd numbers very frequently. We test a minimum size of 3. So I control the strategies to what hypothesis shrinks to or test more frequently. And it immediately catches it, right? And so there's a pull request there. You can click over and you can see the explanation. But like what I did was I changed the input space. I was like, I don't care about the complexity of array names, where they were stored, or their attributes. I care about the size and the chunking. Those are the complexities that I care about for this test. And doing that was very, very important. It immediately catches it, right? And this is why, the big lesson is think about your strategies. Okay, so we've mostly hit most of these again, but just to reiterate, property tests don't replace other tests. They're not comprehensive. They don't prove anything about your code. They're meant to help you increase coverage, in my opinion, and they help you think about the problems. It's like I find it like a tool for thinking and for understanding the implementation. If someone else has done something, like writing a property test lets me, understand it. A point that's come up many times, we are pseudo-randomly sampling the input search space. Like we leave all these details up to hypothesis about how it does it. They keep changing things. They change their heuristics. This means it's upon you to narrow the search space to interesting regions. And I gave you kind of a concrete example. Hypothesis has a lot of APIs to help you do that. But it is on you to do that bit of thinking. Generally, you want to minimize the search space along dimensions that are important for the property you're testing. So for that example I gave, I should have been working with size and chunks and not anything else. The rest of it is not very important. A successful test does not prove anything, as we mentioned. You want to use CI. So here's every night we run 30 minutes of hypothesis CI tests. These tests like 1,000 examples or something, like randomly generate. So every night is like a different run, doing different things. And if it fails, it will open up an issue automatically and stuff like that. So hypothesis is pretty great for integrating with CI. The simple properties are really effective and they're very elegant. I hope I've communicated that. Like those properties that we wrote down were very simple statements. The complexity is all in the generation and the input space. I'm thinking about that. I have found that property testing suites are basically an empirical specification for your program's behavior. So if you don't like it, and like if you find yourself having to exclude too many things, it's a sign that something's wrong. This has happened to me before. I said, this is way too complicated. If I can write a property test that tests some behavior, like a user is getting confused for sure. It's basically a really good empirical check. A unit test that you've written is most likely a property test in disguise, if you just think about it slightly differently. And so Manish showed us the parameterized decorator that lets you explore some space. You could rewrite that as a combination of given and example. So given is just the random space exploration. Example is the concrete, example unit test that you want to run that you like. Best piece of advice for you is if you find a bug, try to construct a property test to catch it. Right? Just try it. Because it takes a little while to get used to the shrinking and the writing of strategies. Beware, it can lead to overconfidence. I definitely learned that the hard way, and they definitely don't replace other tests. Like you need everything else. So happy to take questions at this point. I hope you got something out of it.
Hey, it's time for lunch break, and I think we asked questions during, so I'm going to go ahead and let people break for lunch, and you can catch Deepak at lunch or this afternoon, or email him or anything like that. As Alper said, lunch is in the cafeteria. If you don't know where that is, follow the general flow of NCAR people who are going to go to the right and down the stairs and around. You can go through the line, purchase your food, and then the left side of the cafeteria is reserved for us, so we can all kind of intermingle and maybe talk to someone that we don't know. And I'll see you back at 1:20. Thank you. You don't want to cut off.
You got this.
Question in chat, wanted to look at it. I can also send it to you.
I guess I should.
Make this morning is if you're wanting to use the female restrooms, the one on the second floor, it wasn't just temporary closed, it's like gonna be closed the whole week. So you have to use the one going down the stairs, they pass on the way to the cafeteria. And they're remodeling. But if you go, it just looks like they might be cleaning or something, but they're not. It's never gonna be open. Okay, I'll let Alper start.
Are there ones by the sign-in desk too?
Those are, the men's are by the
ones, the handicap one upstairs.
So yeah, on the second floor, if you go to the left, there's a all gender.
Yeah, right.
And, but if you go to the right, the women's one is by the library is clerks. Anyway, if anyone has any bathroom questions.
Thank you.
Are you good? Cool. So we're going to kick off the afternoon session now. So the title is Bounded Formal Verification. In the last lecture, Deepak advised us to sometimes, take a step back, look at the big picture, think about properties, think about abstractions. So in this lecture, we're going to take that advice to an extreme, and we'll work at an abstract space. And so this lecture, we've originally scheduled this lecture for Phil Zucker, who was going to be here and give this lecture. Unfortunately, he had to cancel his travel, and I'm seeing him online. So if I say anything wrong, if I am not unable to answer any question, I hope he can step in. But yeah, so let's kick off. So you've seen unit testing, we see property-based testing, and one of the common questions was, like, how sure are we if our tests pass? And there's always this shortcoming that testing is not a proof of correctness of our software. So here we're going beyond testing, and we're looking formal verification. We'll actually prove mathematically that our algorithms are correct. And the way this works is we'll first encode our computations and properties. So we will actually model our program, and we'll use this tool called Z3. It's a theorem prover / SMT solver. And I won't get into what those words mean, but it's a powerful solver. That's all I'm going to say, and I'll show how it works at a fundamental level. But what this tool gives us is symbolic reasoning about all possible inputs, not just select inputs, not just random inputs, but it's going to happen in a bounded scope. And then we'll explore some strengths beyond testing, but also some limits of this technique, and then see how this technique may complement testing whenever it's feasible. It's not always feasible. So let me first describe what formal verification is, in case you're unfamiliar with the term. It's using mathematical and logical reasoning to prove or disprove the correctness of a program with respect to a specification. Here again, specification is something quite critical. In fact, it's even more critical here because not only are we specifying the properties, we're also actually specifying our computations here. And the specific formal verification technique we'll use is bounded formal verification, where we'll check properties over a limited set of problem sizes or input ranges. But still, it'll give us guarantees that testing cannot match. And these guarantees will come at a cost. We'll have to encode our code. We must write down precise specifications and model the program's behavior. And these solvers sometimes suffer from what's called state explosion problems. Since they take into account all possible states, the state space exponentially grows, and sometimes the solvers are unable to, fully exhaust all possibilities, and it can become slow or intractable. But where this shines is on critical routines, where correctness is paramount, and on core algorithms, where we might not be able to fully reason about through tests. And this technique can still be practical, not always, but sometimes, when you code your design with the right abstractions, with the right level of decompositions and specifications, the themes that we went over this morning. So there's this additional benefit of going through this effort, and it's that the act of writing specifications and reasoning about them often exposes bugs, exposes ambiguities, exposes hidden assumptions, or gaps in your understanding of the problem before you even run the analyzer. While you're modeling your code, you realize your mistakes before even feeding your model into these solvers. So why bounded? Well, formal methods rarely scale to arbitrarily large programs. This is especially true for automated solvers like Z3. And for instance, we might only be able to prove the properties of our heat equation solver for small meshes, where we work with, say, at most 100 cells. But that's still often enough, thanks to what's called the small scope hypothesis by Daniel Jackson, who says a high proportion of bugs can be found by checking a program for all inputs within some small scope. So one interpretation of this hypothesis is, say you have a mesh that has millions of cells and you find a problem. There is a great chance that you can reproduce that problem with a mesh that only has a handful of cells. So that's the idea here. And so again, in unit testing, you handpick some test cases that you think of. In property-based testing, you randomly sample the input space. In theorem proving, you perhaps can't go as big as property-based testing in terms of domain size, problem size, but what theorem proving / formal methods gives you is this scope completeness. You check for all possibilities within that small scope. And even such bounded proofs can expose subtle bugs or confirm that a property is guaranteed. So again, the tool that we'll use is called the Z3 solver. It's a popular solver, perhaps the most popular formal methods tool developed by Microsoft Research, and it's widely used in academia and industry. It has a broad range of use cases, including bug finding, program analysis, symbolic checking, verification of software and hardware. It's used in compilers, optimizers, and it's used in tool development as well. I mentioned in the morning that the visual case scan tool, and if I should click on this, so this tool is a configurator for our community Earth system model. What it does is it guides users towards valid climate model configurations. And so the way this works under the hood is that we use Z3, and we use Z3 to, resolve or reason about the interdependencies and incompatibilities between different model settings. So here we'll use this tool in a different context where we will prove properties of our heat equation solver by encoding it in a different paradigm, and we will study its behavior and desired properties as logical formulas. So here's the follow we'll follow. Here's the workflow we'll follow. We'll declare some symbolic variables. These will correspond to the variables that we have in our scientific applications. We'll encode some logical formulas. These will be in the form of constraints. And these constraints / formulas will correspond to some preconditions, and we'll also encode our code as a constraint or as a set of constraints. And then we'll state our desired postconditions. We can then ask this tool to check whether our code entails the desired postconditions given the preconditions. And Z3 will exhaustively search for cases where this property Q doesn't hold. And if it can't find any issues or any counterexamples, then we basically mathematically prove that our specification of our algorithms are correct. So the key advantage, testing samples some inputs. Formal verification, in this case Z3, reasons symbolically over all inputs within some specified bounds. So again, remember we have this 3-step workflow. First one being declaring variables. So Z3, when we're working with Z3, we need to work with symbolic variables, and it comes with these types, including integers, reals, booleans, bit vectors, arrays, and more. And these are, again, not ordinary variables. You can't set values to these variables because they are symbolic. And they represent all possibilities of that type. But what we can do is we can constrain the values that they can represent through logical constraints. And they become meaningful when we add those constraints. So here are some variable declarations. And to declare these variables, we use these constructors from Z3, bool, integer, real. And here I am declaring P, a Boolean, I, integer, X, real. And sometimes this can become tedious. What we can do is we can also declare multiple variables at the same line using the plural versions of these constructors. So PQ now is our 2 Booleans that's returned by this constructor. And we can also create arrays programmatically using Python's list comprehension syntax. So here I'm defining an array of symbolic reals. It has 10 reals, and then I can access these using this standard indexing notation. So notice we specify these names in both the left-hand side and in the right-hand side. So the difference here is that the names, these strings on the right-hand side, are the names that Z3 uses internally. And these are basically objects pointing to those internal symbolic variables. And these names don't really have to match, but it's a good idea to keep them consistent. So after having defined those variables, now we can actually work with them. We can encode and check some constraints. And we can express logical formulas over them. And constraints will model preconditions, program logic, and computations and post-conditions, and we'll add these constraints to a Z3 solver object, an instance. We'll then ask the solver whether those constraints are satisfiable. So I'll quickly demonstrate what all these look like in practice. So here I'm importing the solver class from Z3 and instantiate a solver object that I happen to call S. Now I'll also declare some variables, say X and Y. Let's make these some reals. And then now that I declared these variables, I can specify some constraints, some logical formulas. So that's what I will do, but maybe I should contain these constraints in a list. And I'll say x squared minus y greater than 10, some logical mathematical formula, some constraint over the values that these symbolic variables represent. And then x plus y is greater than 0, some random specifications. And then what I can do with these constraints is, good catch, s.add constraints. And then what I can do is I can call the check method of this solver, and let's see what happens. Of course, I did not import reals. Maybe I should first execute all these cells. Okay, so what does sat mean? It returned sat. So in this lecture, you'll hear a lot about sat and onsat. What sat means is it means satisfiable, which means there's at least one assignment of these variables x and y that satisfy these two constraints. And onset means the opposite. Solver tried everything but couldn't find values for x and y that satisfy these two constraints. So what I can do is I can ask the solver to return an example. Because this is satisfiable, solver is able to return one such solution. Y equals 5, x equals minus 4 happens to satisfy these two constraints. I'll try to break these constraints by trying to make it onset. Let me see if I'll be able to do that. X, Y. I don't know. Well, this will maybe, no. But this will definitely make things onset. Yeah. So that's the idea. You give it some logical formulas, the solver, and the solver returns set or onset, and it can also return some counterexamples. So this is the whole idea, and I promise this will be useful in reasoning about programs. But before I get to how we reason about programs and algorithms using this whole mechanism, I'll also mention that when we worked with this example, we used standard Python arithmetic and comparison operators. Z3 uses, or overloads rather, all these standard operators. But for logical operations, it provides some special functions and or not, because these are, I think, not overloadable or something. But similarly, for some other operations, Z3 provides special functions as well, like square root, absolute, concat, etc. But then there are also some kinds of mathematics, some kinds of capabilities that fall outside the built-in theories of Z3. One example being transcendental functions, but we can approximate or model these, and that's outside the scope of this lecture, so I won't get into that. But here, we have two examples that look very similar. Let me solve the first one. It's quite simple. we have this quadratic equation, and let's ask Z3 to solve this equation. So what I'll do is x squared minus 5x plus 6 equals 0. Well, let's run this set, meaning that it was able to find some solutions to this equation. Let's ask the solver to return one such example. X equals 2. So x equals 2 happens to be one of the roots of this quadratic equation. And we might wonder whether there's another root. And the way to check whether there's another root is we can add a constraint, x not equals 2. So that's set as well. And the other root happens to be x equals 3. So quite simple, quite intuitive. But this is also a paradigm shift. When programming, what we do is we instruct the machine to do some stuff. Here, we tell the machine the problem, and it solves it for us. So here's another example in the same spirit. So I'll give a couple of minutes in case someone solves this example, but just to read it out. So there's this formula that models the equilibrium surface temperature of a simple planet. And here I have 4 variables. We know the values of these 3 variables, and we are interested in finding out what the equilibrium temperature is. And so what you'll do is you will encode this formula here and see what happens. So I've already defined the variables. So I'll give it a couple of minutes in case someone comes or finds out what the temperature is for this idealized planet. Anyone close to getting the answer, or did you find out, Mike? What is it? Okay, cool. So I'll do it. One minus A times S or 4 is going to equal sigma times T to the 4. And then I'm also going to encode these values, 0.3, 1361, and sigma equals 5.67 e to the minus 8. Is this enough, or do we need more constraints? Let's check. Is that S or? These are not assignments, but formulas. Okay, so it's set as the S-dot model. Oh, so I made this mistake. This is a markdown cell. That's why it doesn't work. So I'm going to actually introduce an actual code cell and do S-dot model. Okay, so the result is minus 254. Remember, this was Kelvin. So there's a mistake here. Kelvin is an absolute temperature. So what I forgot is our temperature needs to be greater than 0, greater than or equal to 0. So rerunning this, I get the actual answer. Because T has this even power, negative of this value is also solution. So this is kind of a demonstration of how precise you need to be while specifying these kind of constraints. I would think so. Okay, so this is all declarative, meaning that you express your problem and you don't express how to compute things. We didn't tell the solver how to solve a quadratic equation or a polynomial. It was able to find out the answer by itself. And so this makes it declarative, not imperative. And along the same lines, we don't assign values to variables. We constrain them with equations, inequalities, or logical relations. And a couple more examples. So if we want to simulate a case where we assign x to 0 or 0 to x, we do that through this logical formula. Similarly, we can do something more general. This is the power of Z3. You don't have to specify, concrete values. You can also be somewhat ambiguous in terms of, modeling these variables. And these logical formulas don't do anything by themselves, but once we add these into those solver instances, they become meaningful, and Z3 will try to find values that make them true. So here I'll stop for any questions if there is any, but otherwise I'll move on to how we actually use this mechanism to reason about code. Jesse?
Sorry, I came in a little late, so I might have missed this, but like, are these, when you're declaring things as real or integers or whatever, are these like the mathematical definition of reals or like the, or like floating point definition of reals?
Good question, and yes, those are mathematical definition of reals. And then I'll follow up with the distinction and how we can also use floating point in the same manner. Cool. Okay, so remember this simple example, division. We have a precondition, y not equals 0, some computation, and we're checking whether computation was correct. So this is an imperative program. We tell how this computation needs to happen, but Z3 is declarative, so we can't do that. We can't feed this program into Z3. What we can do is we can model this same thing in a declarative way, and what we'll do throughout the rest of this lecture is we will write counterparts of these original functions such that they return a list of constraints or a list of formulas modeling the original code. So here I have that counterpart, the declarative version of division, where I return these three constraints. The first one corresponds to our precondition, the second one corresponds to the computation, and the third one is the postcondition. So now we can check whether the postcondition is correct by simply creating a solver instance, declaring the variables that we were going to pass into that division function. And since this division function returns a list of constraints, we are adding that into our solver, and we check whether these three constraints are satisfiable. Set. So what does this mean? This means that the solver found at least one assignment of values for result x and y. So that's not actually a proof. We just showed that this function is true for at least one set of inputs. To actually prove that there is no undesired behavior, what we're going to do is we're going to flip the logic. So we will tell the solver to find for an example where our postcondition is not satisfied or is not maintained. So everything else is the same here. The only difference, and this doesn't have to be and, this could be a list too, and I'll mention what and is. But so again, the only difference here is that we are negating the postcondition. And let's see what happens now. Same thing. Now it's unset, meaning that solver tried everything, but couldn't find a case where the precondition and code was satisfied, but the postcondition was violated. So this is basically a mathematical proof that our division operation is correct. And you might wonder, as Jesse mentioned, why we couldn't find that floating point issue because we worked with reals. So this is where I will make the distinction between reals and floating points. So real arithmetic is exact, so that's why we couldn't find the issue here. But floating point is not, so that's why Z3 didn't see the earlier 7/25 counterexample that we were able to find with the hypothesis, for instance. But reals are still good for proving the conceptual correctness of our algorithms and mathematical properties of algorithms. Floating point, which is available in Z3, lets you model the IEEE semantics in a very specific and precise way, but it's heavier and harder to reason about exhaustively. So I'll quickly go over how I could do the same thing with floating points. I'm not going to get into the details of all these utilities, but this is kind of a demonstration of how precise you need to be when you're reasoning about floating point behavior. Maybe just to quickly mention a few things here. So I'll choose a floating point format. In this case, I'm choosing half precision. I could go with single precision or double precision, and this would work perfectly fine. But with those higher precision levels, proof takes longer, so I'm gonna keep things efficient here. Then since now we're working with floating point, we can't do exact equality, so I'm defining here an approximate equality function as a helper. And then the relative tolerance here I have is, again, perhaps quite big. Again, that's for efficiency reasons. I could reduce this, but then it would take longer to prove this division function. So I'll run these quickly. So this time, this model of division has this specialized FP is 0 instead of that easier y not equals 0 because we're working with floating point now. Result computation is the same. Here, the post condition, I'm using approximate equal. Otherwise, I have a solver. Then I declare these symbolic variables to be floating point. And S is half precision as I declared it here. And then I'll pass this function into our solver and check what the solver returns. So SAT is something we don't want to see because SAT means that the solver was able to find a case where our post condition was violated. So let's see what that counterexample looks like. Okay. So this is similar to how property-based testing works. It gives us some random examples. But looking at the example, we can kind of see what the problem is. The y value is quite large in magnitude, whereas x is tiny. So we're probably having some sort of overflow, underflow kind of issues. So I'm gonna use my cheat sheet here. So this is a logical expression to prevent overflow, underflows, and subnormals. So I'll add it here as one of my preconditions. I haven't imported implies. I'll do that. Does it say not recommended? I need to remind myself why I did it that way. Well, maybe there, yeah. Okay, so I had another version that I did not recommend. I changed it, but I forgot to change the comment. Okay. So after adding that precondition, I'm still getting some counterexamples. Let's see what happens. Okay. So y is negative infinity, x is negative infinity. So this is similar to how hypothesis gives you these corner cases, edge cases. So I'm gonna have to eliminate this case as well. So I'll add, this is the infinity case. I'll add this precondition. And sure enough, it will return me a case where X is NaN, so let's also prevent that. Okay. Okay, so now this is taking longer, which is a good sign, because if there's a problem, it usually is quick to return that problem. But now it's crunching through all those possibilities and it's just finished. And now it's unset. So we basically proved the correctness of our algorithm under these preconditions. If we satisfy these preconditions, then we have mathematically proved that our post-condition holds. Okay, so as you have seen, modeling floating point behavior is a bit tedious. So what I'll do moving forward is, for our purposes, I'll stick to reals. And I will argue that it's still useful. First of all, it's simpler and faster for Z3 to handle. And it also abstracts away round-off details and lets us focus on the conceptual correctness, which is something, in my experience, that's generally overshadowed by floating point complications. So we generally, don't look at our machinery, our conceptual correctness, and look at numerics and floating point precision to conclude whether our code is robust, reliable, or not. And we can always go back to floating point issues, can handle those later with either testing, property-based testing, some other way of testing, or targeted analysis, even using Z3. So the insight here that I think supports sticking to reals is that if a program is incorrect over the reals, then it is incorrect in floating point. So it probably makes sense to first check whether your program is correct over the reals. Here's another check mark in case there's any questions. Okay. So now I'll move on to the heat equation solver. Remember our three-step workflow. We're going to declare some symbolic variables. We will encode our solver declaratively using some constraints corresponding to preconditions, core procedures, post-conditions, and then we'll ask Z3 to prove the properties that we've been working on and mathematically prove those properties by checking satisfiability of the negation of them. Remember the telescoping property. The sum of the divergence over all cells must equal the net flux through the boundaries. So these are the imperative original versions of these two functions. Divergence is our computation. Telescoping is our property specification that returns true or false depending on whether this property is satisfied or not. Okay, so we'll express these in Z3. We'll define corresponding functions that operate on Z3 symbolic variables and will return constraints representing their behavior. So divergence. Here is the declarative way of specifying the same computation here. C out equals Fi minus Fi plus 1 over dx. Quite similar, same idea, except instead of assignment, we are using equality. That's pretty much the only difference. In the case of telescoping, it's even more similar. The only difference between the original version and the Z3 version is that here we have approximate equality, but in the case of telescoping, it's exact equality because these are meant to be reals, not floating points. Okay, so the two main differences again is that the imperative version uses assignments. In the declarative version, we use equality constraints. The imperative version uses approximate equality, but in the declarative version, we use exact equality. And now it's time to declare some symbolic variables that we can then pass into those declarative versions. Here, I hard code the number of cells to be 3, but down the line, I'll also make this a parameter so that we can play with other numbers of cells. dx dt kappa, these are reals. F and C are our vectors, symbolic vectors. So I'm creating a solver instance, and I'm adding this precondition. Dx is greater than 0, dt is greater than 0, kappa is greater than 0. And this is the only thing that I say about these quantities. So what that means is that we are taking into account all possibilities of dx, all possibility of dt, and kappa that's greater than 0. So this is the kind of power that we get with this abstract specification and generalization. So then I add this divergence function into the solver by passing those symbolic variables. I'm also adding this postcondition where I ask the solver to find an example where our telescoping property gets violated, and then we check satisfiability. So let's see. I probably need to execute all of these. Onset. So solver tried everything, but couldn't find a case where our telescoping property gets violated. So we basically mathematically proved, at least over the reals, that our algorithm entails the telescoping property. But we did this for all valid inputs, for all dx dt kappa, but where n is equal to 3. So let's attempt to increase n, see how Z3 handles larger mesh sizes. So here is the same code, except now I turned this into a function where I can call this function with different number of mesh sizes. And here I am calling this function that I just defined with different numbers of, increasing numbers of mesh sizes. And let's see what happens. Onset is not defined. I must have forgotten to execute a few cells from Z3 import onset. Okay, so for small sizes of mesh, it only takes a few milliseconds. But as the number of cells increases, notice the time it takes exponentially increases. So this is pointing to the case where when we were doing this exhaustive analysis, we need to keep things, small so that the state space doesn't explode. Okay, so we just proved the telescoping property. Now let's look at the other few properties that we looked at in the unit testing and property-based testing lectures. To do so, we'll need to specify other core procedures as constraint generators. So remember, this one was the one we initially specified. For the other three, the idea is the same. We return these lists of constraints that model, that represent our computation. Boundary condition application is quite simple. We set the flux at the left-hand side and at the right-hand side to the boundary conditions that we pass. Diffusive flux, again, this formula, but now it's not an assignment, but rather an equality constraint. And step heat equation, this is the time stepping where we update the temperatures based on the divergence that we compute with the divergence function. So we'll use these declarative versions of the core computations, and we'll prove the other remaining properties. But before that, we're going to have to define our symbolic variables. Remember, we have these reals. We have these boundary conditions that we have just introduced, because now that we're broadening our horizon and looking at multiple functions at the same time. And here's a helper function that I define to allocate these vectors, symbolic vectors, in a convenient way. Okay, so now we're ready to reason about the conservation property. So here's the specification of this property. left-hand side is where we compute this heat content over all the mesh. On the right-hand side, so this is the new heat content. And on the right-hand side, we have the old heat content plus whatever we get from the boundary conditions. They must equal, they must, have the equal values. So I'll execute these. What else? All right. Now, again, it's the same idea. Instantiate a solver, allocate some arrays using this allocate vectors helper, add our preconditions, add of all of our core computations, and then ask the solver to find a case where conservation is violated. So we get unset, meaning that our computations happen to be preserving the conservation. There weren't any counterexamples violating this property. And so, but we did prove this for only a mesh size of 5, but that's an arbitrary mesh that represents pretty much all possibilities that has, 5 cells. And so that's the spatial generality that we get, but there's also this temporal generality. Here we are modeling a single time step, but that time step is an arbitrary time step that represents any time step of the simulation. So by induction, if we prove that our one time step conserves heat, then the entire simulation must also conserve heat. Think of this as a loop invariant, and remember the discussion we had with the property-based testing. Although, of course, there's a caveat here. We are not taking into account floating point round-off issues or local truncation errors that might be associated with numerical approximations, which could actually accumulate over many steps in a real implementation. Okay, so a couple more properties that we'll go over, and then we should be done with the theorem proving part of the tutorial. But yeah, so the symmetry property is, again, just to remind everyone, if we start with the initial state that is symmetric, and if the boundary fluxes are anti-symmetric, having equal magnitudes in the opposite directions, then we must have a new state that must also be symmetric. This is an intuitive property that we would expect from our solver to maintain. So the way we encode this is, so we have this is symmetric function here that returns a list of constraints that checks whether our values are maintaining or values correspond to a symmetric state. In fact, this should probably go to just n/2, but I'm not going to mess with that now. Anyway, so what I'm going to do here is I'm going to allocate vectors again for a mesh size of 5, some positive arbitrary parameters that we will need. And I'm stating here that our initial condition is symmetric and our boundary conditions are anti-symmetric, having the same magnitude but in the opposite direction. Then I ask the solver whether I can end up with a not symmetric new state. So let's call this. I need to import and from Z3 import and onset. So again, I've just mathematically proved that our algorithms maintain the symmetry property. Next, let's look at the monotonicity. Again, diffusion smooth. So one way to express this intuitively is check whether if we start with a monotonic state, do we maintain that monotonicity? So here's again one way of specifying this state. We're checking whether our temperature field is non-decreasing, so I'll execute that. And then here we have this solver machinery again. We're initializing a solver, allocating some vectors, preconditions, computations, and then I'm asking here if we start with a non-decreasing profile, this is the old temperature profile, is it ever possible to end up with a not non-decreasing profile in the new state? And this time, solver actually finds a counterexample. That means that there's a case where this property gets violated. And if I look at the model, now that I have a lot of variables, the model returns values for all these variables. But so if you look at dx, it's equal to 1, kappa is 1, dt is 1. So this intuitively suggests that we have a time step dt that's quite large relative to dx and kappa. The thing is, we did not include in our precondition this stability condition. And it turns out, actually, mathematically, for all the previous properties that we satisfied, that precondition is not necessary. But for this monotonicity property, that happens to be necessary. So I'll add it here. And rerun it. And now the property is proven to be holding in the existence of that stability condition as a precondition.
How'd you figure that out?
Figure.
Just look at the values and try to.
Yeah, so I've looked at the model. That was my intuition. There must be some kind of stability issue if the monotonicity is being violated, because if you're violating the monotonicity, so you probably have these spikes that you encounter in unstable solutions. But yeah, that's that. I think this is the last property I'll talk. Yeah.
What if you didn't have any intuition about, is there a way it could say this only happens? Did it tell you the stability condition somehow?
I think not. But I'm sure there may be some ways of probing these specifications in a way that things are more revealing. But yeah, I guess, yeah. So one last case here, positivity. If you're starting with a state where all your values are positive, and if you have isolated boundaries, then you should remain positive. I think that's what it says here. Expect, or you don't have to have isolated boundary conditions. Non-negative boundary conditions should also maintain this positivity. So that's what I'm specifying here. All positive, allocating vectors, specifying preconditions, injecting the models of our computations, and checking whether this property is an invariant. This time taking a little bit longer. Yeah. So this asterisk here indicates that it's still running. Okay, so now it's done. And it's unset. So we proved this property as well. All right. So the summary part. Okay, so what we did, we re-expressed the solver's core procedures as constraint generators. These are abstract specifications modeling our actual computations. And we use this tool, Z3 solver, to prove some universal identities, some invariants, some properties. And we found some counterexamples when we missed a specification of a precondition and confirmed that fixes the adding the precondition fixes the issue. And so there are, of course, some limitations here. Scalability, we can't work with arbitrarily large problem sizes or with more complex properties. There's this encoding effort. You translate your code into a specification, and there's always a chance that you might misrepresent things. And but still, writing down specification is usually rewarding in a way that when you're writing things down, your code, your intent, you find issues, bugs, or misunderstanding in your own conceptualization of your code that you're building. There are also some theoretical limits, like I mentioned, the transcendental functions, and there's also this chance of some properties being undecidable or intractable. So those are all the downsides. But again, despite all these limitations, there are some benefits. It uncovers subtle bugs. It's exhaustive. It has this exhaustive nature, looks at every case, and it can provide strong guarantees about correctness within specified bounds. But again, there's this caveat. There's this potential gap between the reality and what you're modeling. But again, another side advantage here is that it encourages you to think precisely about your code, writing down specifications and thinking rigorously about the program behavior. Okay, so one last word. There's no one-size-fits-all solution. Certainly, this technique is not a general solution, but having multiple tools, having multiple techniques at our disposal can allow us to mix and match approaches, techniques, tools based on our needs or constraints of the project. So with that, I will stop. Dominic asks, is it not possible to leverage overloading more in Python to have only a single implementation rather than two? Maybe Phil can chime in, but I know there are some tools, to bridge that gap. But yeah. Sometimes, he says. Yeah, some things in Python are not overloadable. I think the logical operators is one of them. Yeah. Yeah, I think that should answer that question. Right?
So I'm thinking about how you would use this, and the impression I get is that because you have to rewrite your code in terms of the Z3 framework, it's really about understanding your problem and kind of modeling it. So one of the practical things I'm thinking about is how do you like store these Z3 example? I mean, how do you keep it up with your code and that sort of thing?
Well, I think that's a question about how you, practically approach this. Yeah. What I would do is to maintain a specification module alongside our code that we can, so this is perfectly runnable in a CI/CD framework, right? We can run these and check. Yeah, so it's just a matter of how you set up your development workflow and environment, but that's perfectly doable. Cool.
So if you change parts of your code, you might need to change Z3 code as well, right?
Yeah, so there's always that gap there that you need to keep things consistent. Cool, all right. With that, is there some discussion going on? for perspective, what percentage of your visual case gen lines is theorem proving? So the logic solver is fully relies on Z3. So I don't remember off the top of my hand how many lines of code is that, but really the core there is the logic solver, and that fully relies on Z3. So another comment by Phil. Okay. Yeah, he has this nice tool, knuckle dragger, along those lines if you want to check. Phil, rather than typing in, do you want to, unmute?
Yeah, can you hear me?
Yep.
Yeah, I mean, I love Z3. I think it's like the coolest thing ever. And so I played a lot with like overloading things and tricking it and trying to make it like, I do think being able to run regular Python code and exactly as it is and run it in Z3 exactly as it is using overloading is like a really cool thing. For numerical stuff, that's more easy. The if then else, if elif else in Python is not overloadable, nor is the keyword and or. You can override the and or operators as Dominic mentions, so you can do that. So it can be done. There's also symbolic executors for Python code itself. ESBMC, for example, is a tool that can actually symbolically execute Python on its own. But then you're not really directly interacting with Z3 yourself. There's sort of a lot of layers in between.
Thanks. Okay, so should we conclude this? Cool. So we're gonna have a 30-minute break now, I think, maybe 35, and then yeah, Adrianna will have another guest lecture where she will bring us again back to the reality, where she will work on an actual real world problem. Yep. So, well, hope to see you all back.
Okay, let's get started again.
Maybe at least it could do something.
Now, our last section of today is Adrianna Foster, and she'll be talking about functional testing first, and then we'll have a practical session. So,
thanks. Yeah. Thanks. So the functional and testing are both hotly contested terms related to what I'm about to talk about. But anyway, and then from various people at NCAR and then in my own house. But anyway, and also I'm going to apologize that this is going to be a very land biased talk. So we're going to talk about a lot of land things. So I'm sorry for you atmosphere and ocean people, but the land is important. So, but we can apply it to all things. Okay. So yeah, we've been talking a lot about correctness, reasoning, which is really great. And I think, sort of expanded my mind today, but I think, before when we talk about like software testing, you always think like unit tests and like, are we going to get a pass fail from this? Did I correctly check for divide by 0? Did it actually read in the file that I meant to read in? But then that's sort of the other end of the spectrum is like, we're doing science, right? So we want to know that we're being faithful to the scientific underlying processes, right? So we don't just want to know that our code runs and it's correct, but also that it's representing our science faithfully, right? So I'm going to tell a refactoring story. Okay, so here's some code from the Fates repository. This is old. So this is photosynthesis code. We're doing some like quadratic root solving. We don't like this code. It's really badly written. It's not modularized. So we're going to modularize it. Yay, it's so much better now. Okay, that's fine. We also actually found some bugs when we were doing this. There were some things edge cases we weren't catching, so we fixed that. So that's fine. It's going to result in some answer changes, but we're comfortable with the answer changes that happened. But then a scientist comes back and says, hey, actually, okay, so, and this is a plot of GPP, so photosynthesis or leaf area versus photosynthesis. This is what it looked like before we did the refactor. Scientists come to us and says, hey, this output has changed, okay, for one of my sites that I have. And we're like, oh yeah, we've refactored the code, it changed. Well, we ran, is this bug or is this negligible, right? We ran a test. This is global GPP, global photosynthesis, the difference between before and after. This looks pretty negligible to me, right? Like we're changing by like 0.003. Okay, and we're in the land, okay, so I know in the atmosphere that would be like, this would be horrible, right? Okay, the land is a little more relaxed. Fine, okay, we don't really know anything. Okay, but what if I told you that this is the data for that site and it looked really good before and now does that look good? I don't know. So you tell me. Okay, right, so software correctness ensures that the code executes as written, right? But the faithfulness is what we want. The model represents the intended process correctly. And these two clearly, they can drift apart quietly because we didn't catch this, right? This is all made up. Okay, this didn't actually happen. We did refactor the code, but this did not happen. I made this up. Okay, but okay, this is what I'm hoping that functional testing can help you correct. So how do we normally test our models? And I'm speaking from like a CGD perspective. Okay, so on the software side, we've got regression and system testing. We've got some unit testing. Maybe we do some integration tests. On the scientific side, we do model validation and benchmarking. Maybe we do some calibration. Okay, but there's this like middle part we're kind of missing. Okay, so but I want to run through. Okay, so for regression and system testing, right, this ensures that the model produces consistent results. So does the model produce the same, meaning we say a lot bit for bit, when we expect it to? So we run it with different restarts, different processors, updates that shouldn't change answers, right? We would expect bit for bit, right? We do this like every single time we want to do a pull request, we have to do these system tests. But there's no science involved here. We're just ensuring that the code works as expected. It didn't change, it did change, the end. Unit testing is amazing, right? So this tests units of software. We talked about this before. They're well-defined inputs and outputs. We're checking generally for errors. We're generally only testing one or a few methods at a time, and these must have a pass-fail condition. And a lot of times we do these frequently, but a lot of times I've noticed it's more like infrastructure-y things, or we're sort of like are we catching the errors? Are we catching the divide by zeros? Which is all very important. But so this is still mostly ensuring that the software works as expected. There's integration testing. I don't know if we do a lot of that, but this tests interactions between components or modules in the code, ensures that the combined pieces of software are behaving correctly, still checking for errors, still usually pass-fail. I think we do this sometimes. So this is still about software correctness. So at the system level, we're verifying that multiple parts can talk to each other coherently. Okay, on the other end of the spectrum, scientists, we're talking about model validation. So we're comparing production run model outputs to observations. Maybe we have some controlled conditions. This is crucial for verifying that the model accurately represents reality, right? We might be doing model calibration. The different components of an Earth system model might have specific methods or observations that they use. Scientists do this all the time, right? So this is critical, but I think it's really difficult, especially with all these interactive model processes that we have going on. And so my argument is that to sort of bridge this gap, we can use what I'm calling functional tests. And so a functional test still tests small, self-contained pieces of model science or functionality. It uses production code, so not mocks or stubs, and it focuses on behavior and scientific relationships, not exact numbers necessarily. The inputs may be controlled or idealized to isolate one process. And we're generally not going to have a pass-fail condition, but we might compare to expected qualitative or quantitative trends. So we want to say, does this routine behave as the science expects it to, or as this data set that I have says it should? Right, so this ensures scientific faithfulness. The code still represents the intended science, even as it evolves. And so I was talking about this to someone when I was developing this idea, and they said, well, I did this already. I have a MATLAB program that runs the photosynthesis model, and it works great. Okay, I would call that prototyping. It's not the same thing. So functional testing, it uses the established code. Its goal is to evaluate the behavior of that code and check for faithfulness. It's repeatable, documented, part of the testing suite. Prototyping uses experimental or evolving code. The goal might be to explore new ideas or formulations, checks for potential or plausibility. Usually, I would say most times when I see these kinds of things, they're messy, it's non-repeatable, and usually in a higher level language, like Python, right, or MATLAB, not something like Fortran or C, which are, understandably, it's hard to set up. Okay, so this tests the code's scientific faithfulness, the actual production code. I'm going to keep harping on this. This is designing and testing new behavior. So if you tell me that I rewrote, and it's kind of ironic because that's what I did for our tutorial, but I rewrote this, photosynthesis routine that's in Fortran in your model into MATLAB and it works great. I'm going to say, that's great. That's cool, but I don't care. That doesn't tell me that my code works great because it's a different language. You might have translated it differently. Now there's bugs maybe that there's we didn't catch bugs in the Fortran code. Now there's bugs in the Python code. It's not the same thing. So I'm going to die on that hill. But anyway, okay, so anatomy of a functional test for me, we've got inputs. So this could be arguments. It could be driver data. We call the production code. We get outputs from that production code either to the screen or maybe we write some data to a file. We then have some kind of diagnostic, which could be a plot or some statistics. And then we, as the scientist/software engineer, look at it and interpret it. So we're using real routines from the production model, keeping the inputs simple and controlled, and we're evaluating behavior using, either a visualization or a statistical consistency. The output might be a figure or some metric. It's not necessarily like a Boolean fail, pass, fail. Okay. All right. So, and I also want to talk about faithfulness. So here, again, on the photosynthesis, this is our leaf layer photosynthesis subroutine. What do we mean by faithfulness? Well, I want to know that this routine, when I run it maybe over, so you can't really see oh my goodness, what just happened? Changing light over time, or not over time, changing light, changing CO2 concentration, changing leaf temperature. It follows these expected curves that we know from decades of research in photosynthesis in the photosynthesis world, right? That our very simple leaf layer photosynthesis model should be producing these values, okay? Right, so yeah, faithfulness means the code preserves the physical and biological relationships. What we want to know is, does the output respond in physically consistent ways? So slight numerical differences is okay, but we don't want this conceptual drift away from these sort of idealized curves. And I want to kind of step back and talk about field faithfulness in science software. So I don't know, this is looking at a graph of predicted critical beds occupied per 100,000 of population. This is COVID output from COVID sim, which is epidemiological model for COVID-19. So this actually, theoretically, this output from this model, which was run in the early days of the COVID-19 pandemic, was used to justify a lot of the UK lockdowns. And so pretty soon after that happened, there was all these weird blogs who were they got the code was uploaded, and they got the code, and it was saying oh, there's systematic errors, it's totally unreliable code, it's a buggy mess, developed without any ceremony or rigor. The code was kind of one big long 15,000 line thing, and there was a science paper that came out that was no, yeah, the code is maybe not designed with best practices, but it's good. The model is good, the outputs are good. And the author at the time said, hey, cleaning up and releasing the code was not a top priority for us. We were saving lives, which is fair, okay? But so though eventually, several studies backed up the model output, it reduced faith in these epidemiological models and sort of, kind of you could say these are bad faith actors who are coming and kind of coming at the code. We don't want to be, we have these big Earth system models. We don't want to be in the business of defending our maybe less than best practice written code without having at our disposal these nice tests that can say, hey, some guy says, do you even know what this function does? What this giant subroutine does? And you say, actually, I do. Here's some output from it. So, okay, so let's give an example of fire spread related functional tests. So here's an equation a graph looking at fuel depth versus reaction intensity. And this is really important for calculating fire spread. In this FATES model, it's a vegetation model, we calculate fire spread. So we're looking at fuel bed depth, which is just like how deep the fuel bed is, versus reaction intensity, which is sort of like how big is the fire going to be. Okay, so this is the original. Let's say we refactored the code. That doesn't look right? Okay, so this sort of like, we the question we want to say is like, does this still look like what the fire spread should look like? And we can say, no, I think something weird went on. Okay, so if we want to look at this test, so here is, and again, this is going to be in Fortran because the production code is written in Fortran. So again, the functional test itself, it's a standalone program compiled into an executable. So here I have a program called FATES test, ROS, rate of spread. Inside that program, maybe I have some helper functions that read in a parameter file. I also have a helper function that calls the actual test, so test reaction intensity. For that actual subroutine, I just want to harp again. Here, I'm using this SF equations mod. That's an actual module from the production FATES code. I'm using the subroutine reaction intensity. And then I'm doing a really simple, I'm just like iterating over some range of fuel depths, calculate reaction intensity. And then I'm going to output it to a file so that a higher level language can interpret it. I'm done with Fortran. Okay, I don't want to deal with you anymore. So for my infrastructure, I have a Python builder that builds the executables for all the functional tests. So it's just here, run cmake and run make. Then I have a Python script that runs all of the executables. And then for each test, you can create some class with a plotter that says, okay, plot it out, and there you get the output. And then I just want to show you, this is me running this test. Whee! Okay. So it's really, I mean, theoretically, this should be really easy to run. It should be automatable and able to just kind of like run anytime, like say, you don't have to do this every time because, right, this requires effort, like looking at graphs. Like we don't want to do that every time. Yeah, go ahead. Exactly. So that's right. So this is not, the running of the test is automated, right? But the diagnosing of the test is not. So I guess, what I would say, I can talk about this later, is that, one thing that we talked about doing is you can save the output from, so like this is reading in a file when we're doing the Python plotting, it's reading in like a netcdf file that we wrote out and then plotting it. You could do the same kind of regression testing that you do on that. That could be one thing you do. You could also say, I don't necessarily think that the functional testing has to be done every single time, an update happens. Like, let's say like you have a scenario where we make an update. So that photosynthesis story that I kind of made up, we do some refactoring, GPP changes so we say, oh, GPP is not bit for bit. Let's run functional testing because we didn't expect that. Maybe we did expect that to happen. Maybe we didn't expect that to happen. Let's run all our functional tests that we have. Hopefully we have good coverage and we can just look at all the figures and say, okay, they look okay. Or maybe we just run a couple of them. Let's run the photosynthesis ones. And so I think, yeah, the interpretation does take time. And so I wouldn't think that you would necessarily do this every single time you make an update to a model. But yeah, right. I agree. So yes, yeah. Right. And so like here's looking at a few more fire equations. So here is looking at where we've calculated, again, these are production methods. And here are the plots that I output. And then I'm going to then compare them to some plots that we have in a published paper. So we can say like, oh, these are doing really well, right? We're like accurately simulating these responses compared to, what we based the process on. Okay, so now let's go back to looking at leaf level photosynthesis. So here, these are all, again, these are all calls to the actual FATES model. And then I'm going to plot over different, different light levels, different leaf temperatures, B-tran, which is like a measure of moisture stress, CO2 concentration, leaf nitrogen, and then vapor pressure. and then for different plant functional types. Okay, so mostly this looks good, but what's that? This actually did happen. Okay, this is a true story. I made this functional test and we did find a bug. So that we didn't know this was happening. There's something really weird going on at high vapor pressure deficit. And we needed to fix that. And so, you know, you can conceivably think about like, you could do this for a lot of different, so you might, as you're like adding these functional tests, you might find problems in your code. Or maybe this was generated by something that we did, right? Similarly, maybe you have some output at a specific site and we have some data we can compare it to and say like, oh, like we're not maybe doing this very well. Okay, but you know, then when you're comparing to data, yeah, like so our models are really highly interactive, right? So small changes ripple out unpredictably, and you know, testing over a range of values is all well and good. We're exercising maybe one or several methods, but we might want to expand out and test like a whole series of methods. And so applying that across, you know, just like 0 to 100, you know, whatever your argument is maybe not that interesting to you. But that's difficult, you know, when, you know, you might say, well, the only intermediate between, you know, that and like testing how the model works is like full scale model validation. And that's really hard because these models, they're all really interactive. And so like, is my GPP too high because of some reason? Or is my fire too high because there's too much fuel? Or is it too dry? Like there's a lot of things going on. So what we really would like is some sandbox for testing, that like we've got some like controlled realistic test cases or values, not mocks really, but like simplified for testing. So what I did for fire, the Forest Service has this standard fire behavioral fuel model. So these are sort of like these standardized fuel classifications that they've developed. And so they have things like moderate load conifer litter, dwarf conifer with understory, low load dry climate grass. And so each of these, there's like 100 some of them, has like fuel amount, geometry, what's the typical, you know, like moisture of extinction. These are all sort of like fire related variables. And so I sort of turned these into a synthetic fuel type that you can read in to the testing infrastructure and say like, okay, well, I want to look at these 3 models. Tell me what they look, you know, what they look like. Here, this 102, which is the dry climate grass, it's mostly live grass and some dead leaves. The middle one, which is this low load conifer, it's mostly branches and some leaves. And then the last one, the dwarf conifer, is like all dead leaves. And so we would expect these to behave differently if we coded up our fire model really well. So it's not, you know, this is nice because we've got this sort of like way to pick from these realistic but sort of simplified different fuel classes that we can then use and test. And so here's just looking at testing fuel moisture. I also have data from a site in Alaska. This is an Alaska project, but looking at, or the data is weather. And so then from the weather, I can get this Nesterov index, which is a measure of sort of fire danger, basically. And then on the left side, or the right side, we can see the fuel moisture for those different fuel types. And so they're different. We can see when fire danger is really high, the fuel moisture is really low. I mean, this is all stuff that if you were a fire scientist, you'd be like, yeah, great. But it's sort of like telling us, so we could look at this and say like, are we accurately representing these different fuel types? So the 183, this one dries out a lot more slowly than the 164. I'm going to tell you that that's accurate based on its composition. So that's good. For synthetic patches, this is something, so similarly building on that, FATES works as it's a vegetation model. And so it calculates tree dynamics on these different patches. And so instead of having a synthetic fuel, what if we had a synthetic patch? And so I developed that. This is basically, we want to have these like really standardized patches, and these are Fortran types, so like classes, that the patch is a class, but then this sort of like factory gives me a FATES patch, an actual, you know, object from the FATES model, but filled with these really standardized values. So like we've got, you know, 2 trees that are very similar in size and density. So they're an evergreen tree. So this is like an even aged evergreen plot. Down here, we're getting lots of trees that might be in different canopies. This is a tropical plot. And so what we can do is then take these patches and call methods of the patch class, knowing that we're not just using like really sort of dummy values, they're actual sort of realistic but simplified values that you would see in the real world. And so then for integrating into workflows, right, this is the normal integration from like new code, and then maybe you do some unit tests, you definitely do system tests, and then you deploy. And then I guess, as I was saying, like I would sort of see these as fitting in either in here, or maybe after you do a system test and you see that something has changed, you can go back and run the functional test to try and diagnose. So, right, so scientists, right, they care about correctness and faithfulness, right? So it's an understanding. And so functional testing, I'm hoping, is a way to sort of formalize trust in scientific reasoning. And then as your model development proceeds, you can sort of ensure that these relationships don't change unintentionally. Another benefit of these functional tests that I've gotten from scientists is that actually it kind of lets them interact with the code, with the Fortran code, like a very small piece of the Fortran code. They can go in and like change things and then see how it affects like whatever output they want really easily without having to like put in these like crazy print statements all over this like giant, Fortran code. So that's cool too. Right, so that was way faster than I had practiced, but okay, so functional tests, they exercise, right, small units of code again, and they help understand scientific behavior, not just code correctness, generally small, interpretable, and automated. And again, they use production code. Okay, so I want to give a lot of thanks to the CTSM and FATE software engineering team. So Eric, Sam, the Sams, Greg, and Ryan have been really helpful in like helping me create and test and utilize this functional testing thing that I built. Bill Sachs also has been invaluable in helping troubleshoot a lot of things. Linnea Hawkins is a scientist who's been using it a lot, and actually she told me like she's got like 5 other people using it. And then Alper for inviting me to come give this talk. And so thanks.
Can I trouble you to go back like 3 slides to show the waterfall thing?
Yeah.
And it seems like the technique that you're using with the functional tests could also be used with the system tests. It's like you and look and see, okay, do the graphs still look good?
Yeah, but I think our outputs are generally pretty, like if so, like say like something changed, like GPP changed, and globally, like that first plot I showed, like I don't necessarily know why it changed. And I'm hoping that if you write a well-designed functional test, it might tell you, oh, it's changing because this functional relationship has changed. Whereas the output is kind of like this emergent property of the entire modeled system. Yeah.
Yeah, I mean, it's really cool. And I'm curious, because I feel like this is a place where CTSM and CAM share potentially a similar problem, which is that we have a lot of like Fortran subroutines that have lots of dependencies on other Fortran subroutines, and it can like go all the way down.
Yes.
So have you found this motivated scientists to write more modular code, or is it?
It's motivated me to write more. Well, so I agree. Yes, it's so when I started this, like there was a lot. I had to do a lot of, especially the Fire code, which is like all modularized now. I had to like rewrite a lot of it, which I wanted to do anyway. But again, like sort of like I think Alper mentioned this in his tutorial, like thinking this way of like, how would I make this a functional test? It sort of forces you to write the code in a better, more modular way so that we're not like, I'm just gonna like, just throw everything into this subroutine because I might need that whole object, right? Rather than like, well, I actually only needed like whatever, rainfall or something, right? And so I think, sometimes it's in like, that's sort of like inescapable. And for that, you can try to think about like these factories that sort of like create a version of whatever object it is with just the stuff in it that you need, which I've done. And so I think there's ways around just like refactoring every single method that you want to write a functional test for. But I mean, I think it's sort of inescapable and kind of maybe that's not bad. Like maybe it's not bad that we like slowly refactor our code to make it unit testable and functional testable. But yes, I did have to do that.
We do have an online question.
Oh.
It's from Don. Automation is used in this approach to avoid having to look at plots.
Right. Yeah. So far none. And so I think I would love to hear feedback on how we could do that. I mean, you could think about like image processing, but like I said, and maybe, I don't know if Sam has an idea, but all of the tests so far, I think all write output. That's kind of like for my fates thing, that's kind of the idea is like you write a test, it writes output, Python reads it and like does something with it. So you could take all the output and like do the same. You could do a regression test and say like everything's the same. Great. So like we're bit for bit, we're not bit for bit at this emergent level, but like all the functional testing bit for bit. So we can ignore everything that we've tested there. And yeah, Sam.
You can also throw in unit tests
Yeah.
to this.
Yeah.
Right. So like the Python script that you have that processes the outputs and makes a plot, you can also throw in something that says like, for this function that we're testing, we expect the output to be monotonically decreasing, for instance. We expect a smooth function. And you can make pass-fail tests during that post-process.
Which seems easier to do in Python than Fortran.
Which I have actually done.
Oh, great. Okay, yes, I thought you had done stuff like that. So yeah. Yeah. Can you say more about how you interface with Fortran subroutines? So yeah, directly. So this is actually the code. So yeah, the way that this is the functional test. So it's a Fortran program that directly uses the Fates Fortran code. So there's no intermediary. Like we're not like taking the code and like copying it somewhere else and maybe changing some lines and then reading in the objects into some other like Fortran to Python reader. No, it's like we're using Fortran to run Fortran. Then that spits out output to a file, which Python reads in and then the Python is the wrapper that builds it just calls CMake and make, and then runs, just calls, execute the program.
With the test, when you deploy your software, do you install it? Do you install the functional tests, or do you have, make tests as opposed to?
Yeah, so this whole stuff is in the Fates repository in a folder. And so if you do, because it requires, Fortran compiler, and it does require some Python stuff, and then it requires interfacing. Right now, like we need Seam, which is like for the non-NCAR people or non-CGD people, it's like our software sort of like stuff that runs all that. We need Seam to do some stuff. And so there is a little bit of setup if you want to run it on your personal computer, which I've done. But if you want to run it on a computer that already runs the NCAR models, you don't need anything. You just run it. Run the run Fortran functional test script. And so that is not automated. You have to actually go in and like type that command. But one of the Fates software engineers is working on running those to be a GitHub action. So that would be cool.
Documentation for it.
Yes. And I'm trying to make it better. If you're interested, you can go to the Fates repository, which I should have put a link up for the Fates repository, but yes, I do. And yeah.
I guess I have two questions. It seems so cool, so impressive. So is like the data, does this testing framework store any of that like reference data, or that's on you? to-
No, that would be, so right now, we don't have any reference data that we're comparing to. Right now, we're just kind of like saying, like, does this pass the sniff test for what we think this curve should look like? It does have, one of the tests uses driver data, the like weather data or fire data, fire weather data. But no, it does not. It could conceivably, like, you could store some, like curve somewhere and say like, hey, are these like basically the same within some tolerance? Like that could totally, and I think that's nice about, because a lot of times like Fortran is great. I didn't wear my Fortran shirt, right? But like it's harder to use, right? Like it's harder to do things in this lower level language, and so which I like. I mean, I'm really biased, obviously, but like for me, I really like that I'm running the Fortran code, right? I'm not, because like some people have said, well, what we want to do is just put everything in Python and like somehow grab the compiled Fortran objects and execute them in Python, which to me feels very error prone. And again, like you're not actually running the production code, you're running it through some weird library that I don't. So we're running the Fortran code in Fortran in the same environment that we would run a production run. We're spitting out output, that any output that we might get from an actual production run. But then we're using this nice Python to just like, let's do stuff to this output. And I think it's not necessarily pass fail, but it could be pass fail. You could think about making it like, okay, like, is this statistically similar to what maybe the last time we ran this, or what we would expect given some data set that we have, or some synthetic data set that we created. Like, I think you could sort of like very open. Yeah.
So like Jesse's question, I'm not, I want to offend any atmospheric field, but having like dipped my toe into that, like one of the things you realize is like so much of the code you might want to test is not really like accessible via the neural model methods. Like it's not an output variable you can output via the
exactly
file system.
Yeah. Well, so so yeah. So I'm writing my own output. So this is almost all of this is stuff that would never see the light of day, right? This is all internal variables inside the code, and then what we spit out is like burned area and how many trees died. This is so many levels before that happens. And then for, you could, I don't know what your system is like, but for me, like I wanted, I just wrote my own netcdf, really very simple IO like helper module to write out the data that I wanted. And I wanted it to be a netcdf just because that's what we normally do. I mean, whatever. And that's easy. That's like a library that exists. I don't want to create a CSV writer for Fortran. That's terrible. So did that answer your question at all? Yeah, so so what I'm not doing here is using like the production IO. Like I don't really care about that. I would expect our unit tests to handle that. So I don't really care about the production IO. What I want is just to spit this out somewhere, and I wrote like a really simple module for that. Okay. So now, unless we have more questions. Okay, so I also wrote a little practical for this, and I translated it from Fortran to Python. But okay, but that was because Python was the prereq, and like it does take a little bit of like finagling to get Fortran code to run. Okay, like I'll admit that. Okay, so anyway, you can access this multiple ways like before. So this is the GitHub page, which will walk you through how to access it. Also, if you want to look at it on your, so I would recommend going to this link because it shows you the code. And then this link will take you to just like a notebook that is like a static notebook. But so I just want to walk through this a little bit. So we're just going to pretend that this thing that sorry.
And there's a link in the
It's not. Oh, yeah. Okay.
Welcome day one.
Oh, I don't know if that was in, was it? Oh, great. Okay, thank you. Okay, so we're gonna pretend that this source code that I wrote is from this giant Earth system model, right? It's really rewritten. I mean, it is, but it's rewritten in Python. But we're just gonna pretend that like it's complicated and huge. And so yeah, the source code is from a handful of methods from the Spitfire modules of the Fortran-based Fates repository. Fates is a vegetation demographics model. It's run within a host land model like CLM here. And the methods have been translated to Python for this tutorial. Okay. And yeah, Fates, yeah, it represents physiological and demographic processes for these individual cohorts that exist on these patches. And then the fire modules in Fates are used to calculate things like fire weather, fuel conditions, fire risk, fire behavior, fire mortality of plants. So they're very important for accurately predicting wildfires as well as overall vegetation and carbon dynamics. So we should be testing them, right? Okay, so now I'm not gonna walk through, I'm just gonna like let you guys loose. And so if you have questions, please raise your hand. And I don't know, feel free to work in groups or by yourself or whatever you wanna do. Thank you. Keep going.
You're just having fun playing around.
Okay. Yeah, I mean, we don't have to finish this now, right? Like we could.
Yeah, if anyone's feeling brain dead and just wants to
wrap
leave,
up.
that's fine.
Yeah,
If you
that's
want to
fine.
stay and ask questions, that's fine. Kind of.
The last one, if you want to just skip to the last one, it makes you diagnose a bug, which I thought was fun as fun. So if you're feeling bored with making me write, having you write plots, but you can.
Yeah. This room is quiet. My new shoes are. I feel like I'm like. Right. I was just thinking about, I do a lot of numerics related work.
Yeah.
In
Yeah, okay, yeah.
And what's more like burgers and marathon burgers?
Okay.
And that feels close to this.
Okay.
Obviously, it's a little different to
Yeah.
say whether it converges at all versus does it converge to like this one.
Yeah, yeah.
It's definitely got that flavor of like.
Yeah.
It's in between, testing and
Right.
system testing.
So I mean, yeah, like you could output the values along the convergence, like as it's getting to convergence, or you could, how many steps did it take to converge? And I mean, I guess I don't know what your,
I guess I was just
because
thinking.
the photosynthesis does have some solvers in it, and so like you can play around with like, how many, what do I do if I don't converge? Like, yeah.
Yeah, I guess there's a couple of things I was thinking of. One is just that any this sort of thing where you look at intermediate values. They would
Yeah,
like
yeah,
you find
exactly.
bugs.
Exactly, yeah.
So we found like, not so much in PLM, but like in the seam ocean atmosphere coupling code.
Because I have
It's like sometimes the iterations just don't converge.
Yeah.
Like they just oscillate forever.
Yeah,
Like,
right.
turns out that the equations
why
don't
I-
actually have a solution. So the iteration
Yeah.
can't converge on anything, so there is no solution.
Okay.
So that was fun.
Yeah.
Sounds good. But
Yeah, so I'll
the
just.
maybe more relevant thing to like this kind of looking at plots diagnosis
Yeah.
is sometimes you get convergence in some regime.
Right.
Like if you're.
Yeah, and that was the
like
problem with
convergence in
the
space or
photosynthesis.
time.
Actually, it was not
Like,
what was happening with this code here.
Right.
Okay, that's what.
That it was at high, so at low humidity or high vapor pressure density, it wasn't converging, and so it just like picked some random value.
Yeah.
And it happened to be like really high, and so we would get this really weird behavior where we would get like really high photosynthesis randomly.
Yeah, okay.
Yeah, so that's what was happening here. We realized it was this weird.
That's
convergence.
supposed to be monotonic.
Yeah, it should be like, it should, yeah, like the data look. Yeah, the data look more like the
Yeah,
trend going down.
it's
right?
kind of gradual.
Right, it should do this weird thing, yeah.
Oh, I'm just kidding. Yeah. Slam. I don't know. That's a good question. You should
I mean, I think
Do
Q stack.
conversion test, change it like the time step.
Yeah, yeah.
In the atmosphere is more you'll get a coarse resolution, like flat or just like not predictable behavior, because like maybe it's saturated at like some limiter kicks in and prevents it from crashing, but it also means the sound is no good.
Yeah.
Yeah.
And then as you decrease the time step that happens less often, you get into this sort of regime where all those mathematical things happen, like you can find all the functions like there's so this thing. Okay. You get like first order, but like different slopes of line, you get first order say convergence. We do on see whether it's getting about the right conversion.
Yeah.
Because it's hard to make a pass-fail test.
Exactly, yeah.
From this set of data,
I won't go to.
like, how big is the sensitivity?
Yeah.
Yeah, right.
How big do we expect it to be? Like, does it have to adhere to first order conversions?
Yeah.
Oh, it's still incredibly coarse, it's like.
Yeah, yes, it's kind of like that.
It says it's like 0.95 order convergence, probably fine.
Yeah.
Like this struggle. So one thing we wanted is for some parts of the code where we should have these kind of guarantees. We want to
Yeah.
have that be part of the testing process.
Right. Exactly.
Okay, when you get to look at this, it doesn't fit into the.
No, it doesn't really fit into like the CI.
Yeah, it is one of
Or like just like a test it go, right? Like just looking at like pass fail output. So like I agree, it does take time, right? Like so like who knows what they're looking for to like look at the plot. Like, oh yeah, yeah,
Yeah.
that's the part that I think.
Yeah.
Add, like, yeah, I just do this little bit. I guess, but yeah.
Yeah.
all this proper code. Always easier to
But
do.
you could think about.
I'll just do this little thing.
Yeah, like if you can see some data, like,
Yeah, right, yeah.
well, is it matching the other data that I made?
Yeah, I mean, people always have to eventually look at the model.
Right, yeah.
So like, yeah, just introducing this.
But I think, yeah, like benchmarking the model at a finer scale, like, okay, well, here's our output, like, whatever it is,
Well,
yeah.
Oh, you know, part of the reason I think of it as related to this is like, thanks for the overall model, thanks for because there's too many special cases and like limiters and things that are not happening.
Oh, yeah.
But there's lots of significant
Yeah.
that should.
Yes,
be more
yeah.
everything,
Right.
yeah.
Yeah,
And it's also
That's a cool
close like
problem.
with more text.
interesting, yeah.
Yeah.
Yeah, I feel like the core ideas are.
Also, just one other comment. My first thought was like, oh, we don't have that many empirical formulas. And then my next thought was like, oh, I've seen the water vapor saturation curves get screwed up. So there's at least one very important step that we've had
Yeah.
before. So
Yeah.
like maybe I should.
For unit testing.
We just haven't thought enough about
It's more physically based, right, so.
Yeah. Yeah. The other thing is
Well, probably not anything.
people tuning the model from what matches lab data or like your best in situ data because it makes the climatology look better.
Right. Yeah, right.
I wish we didn't do that.
I don't think you're thinking.
Because it makes that
dynamic generation test properties.
justify that you're getting grades.
I agree,
But
yeah.
Okay, I should have pointed that out.
maybe, yeah. If we looked at this sort of thing more often. Yeah, it'd be a little less accepting.
Oh, right, we
They get
got-
it in their head that like you're supposed to be a reasonable curve.
Yes, yeah.
And if it's an optic, you're looking at it, like, oh, this should actually. Like messing this up, it should ideally not be the way that we fix some other things.
Exactly, yeah, right.
Or something?
Yeah.
Since thinking about stuff.
I've been meaning to, but
Just
it's
connect
just
the online.
a matter of
Any questions?
non-existent time.
Yeah, that's fine. Yeah, thank you, yeah.
Oh, you just think out now?
Okay, sounds good.
Let's see where I'm.
See. Hi. Oh, thanks.
Something that.
Okay.
Answer the question about is it the model that's wrong or did we code that? And it sounds like this approach might help.
Yeah.
Also, it might not.
It might not, yeah, exactly, yeah. I mean, I think like, right, like you even, I mean, I guess my like probably way too hopeful theory is that if you have like full coverage of functional testing, we have some weird behavior, we can like diagnose it. But I think like, you know, when things start to interact, like there's always gonna be these weird things that maybe we don't catch, but yeah, or like, sure, like in this controlled case, we're doing well. Yeah, I agree. I think it's not a panacea, but it is nice to show like, oh, we do know what this, you know, we're having faith that these methods are like doing what we intended them to do.
So I'm working on this project where we're doing but that's just one, most of the stuff is stuff. And I just don't know how to decompose things to where I can actually do functional testing.
Yeah.
Which is why I asked that question about the system test.
Yeah.
That's where I am right now.
Yeah. I mean, I think it's hard because you can probably, I mean, most of the time we've been able to figure it out. We can where things went wrong, right? But, you know, my hope is that it's easier if you catch it early, right? Before I run, like maybe I run a functional test. I anticipated, I was in this code and like, I just want to make sure.
Yeah, I think we're gonna go ahead and stop. We can stop the recording.
See
and
that
we're gonna
current case,
close
okay,
it
like
today.
something weird happened, right?
So thank you, everyone, and thank you, online folks, and you're welcome to stay in the room. And we can stop now. Yeah. And we'll see you all in the morning.
Thank you.
Thank you.
Okay, cool.